Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. So today, we're going to be working on GPUE, the GPU-based gross Pdfski equation solver. We were working on this yesterday. It was a decently popular stream, but again, these streams are not necessarily about popularity. These streams are about transparency with open source research. And so again, the point of these streams is not necessarily to get a whole bunch of views and like be incredibly popular or entertaining. The point is to do research in an open and inviting way, and that's what we're trying to do here. So if you guys have questions, comments, concerns, anything like that, as we're going through the research that we're doing here, please ask as soon as you have them. My goal is to answer everything as quickly and efficiently as possible, but of course, depending on the question, it might need a more nuanced answer. Before continuing, I do very quickly want to go to a link that I posted. Let's see, where is it? Actually, let me not have that tab up. I think it's this link right here. So recently, let's see, so the Okinawa Institute of Science and Technology, yep, that's the link, has sponsored a video from Minute Earth. Now, I know this doesn't seem like a big deal. Let me put a like on this thing, but it is actually kind of a big deal. So internally, we were having a lot of questions about whether or not we should sponsor content of this nature. My answer was, of course we should, because it's great publicity for the university, yada yada. But of course, procurement section was like, oh, like it's only a 2-minute animated video. We can make a 2-minute animated video. And so there's a lot of discussion internally about whether or not we could or we should make videos of this nature or sponsor videos of this nature. In the end, we were able to get one video out as a test, and so we really want this video to be as successful as possible. So if you haven't already, please just check out that video, see what it's like, and if you like it, then give it a like, share it, all that kind of stuff. That's kind of where we're at there. Hey Jerry, thanks so much for coming in. So again, check out the video. If you like it, share it. We're trying to make it as popular as possible because the more popular it is, the more likely OIST can sponsor content of this nature in the future. And we do want to get OIST research out as much as possible. So if you have questions on that, let me know. The final thing to note is on Twitter, I just put up a poll on a new video I want to make. So basically, I decided I want to make a video on research that I've been doing here at OIST, just research in general. Here's the link to that. So if you want to, please feel free to cast a vote on that poll. I basically said, look, I've been doing a whole bunch of research here at OIST, all of which is basically published. One to do with GPUE, the GPU superfluid simulator. Another general talk about scientific software development and its placement in the general academic environment. Another on superfluid vortex chaos, which admittedly, I thought was going to win out over the other ones just by far, because superfluid vortex chaos, as Fulcher says, I mean, they all sound interesting, but superfluid vortex chaos is one of the coolest collections of words I can think of. I was really expecting that one to win out, but it turns out the one that's been winning out so far is scientific software development. So I don't know if that's just an inherent bias with the fact that I post programming stuff all the time. Not sure. Regardless, please go ahead and cast your vote there. I'm going to be making a new video on my research. I'm just not sure how to spin it. So that's kind of what I'm trying to do. In principle, we'll probably be making 3 separate videos, one for GPUE, one for the Journal of Open Source Software, which is where we published GPUE. It's a very interesting journal that I want to support. Another on scientific software development, and then another on superfluid vortex chaos. So that's actually 4 separate videos. And this is kind of where we're going from there. Again, I'm going to be trying in the future to make basically the research that I do at OIST and the research I do in general as open and clean and clear as possible. So this is kind of the heart of all of this stuff that I'm doing. Okay, so now let me open up Zernal real quick, and let's start talking about superfluids. I apparently accidentally deleted my previous Zernal session, so I apologize for that. Okay, so I'm not going to go into this too much because admittedly there aren't so many people online that were probably not here yesterday or the previous GPUE stream, so I don't feel I need to go into it in that much detail. But if you have questions, just ask and I'll do my best to answer them as soon as I see them. Okay, so a superfluid. Let's start with that. Superfluid. A superfluid is a fluid that flows. A superfluid is a fluid that flows without viscosity. So basically, if you rotate a normal fluid. Let's see, I know I have a normal fluid. I always have my water on me. If you rotate a normal fluid, rather, if you move your hand through a normal fluid like water, you feel some sort of drag force, which is inhibiting your hand's movement. In a superfluid, there is no drag force. There is no viscosity. There's really nothing there that's keeping your hand from moving through it. one weird thing about superfluids is that when you rotate a superfluid, rather than getting a vortex, let me see if I can get one, rather than getting a vortex that looks something like that, where you have like, this kind of conical shape, you get a whole bunch of smaller vortices that go from the top to bottom of your superfluid. That is to say, vorticity in a superfluid is quantized. It comes in quantized units of an extra vortex. You don't get one big vortex, you get a whole bunch of smaller ones that enter one at a time. This is a very interesting thing, and it's something that we've been studying for a while. Most of my research that I've been doing at OIST has to do with superfluid vortex simulations of various natures. One-dimensional, two-dimensional, three-dimensional, all this kind of stuff. It's all related to some form of quantum system that has usually some sort of vortex dynamics or something like that. As such, we needed a very fast simulator to do these types of simulations, so we created the GPU-based Gross-Pdevsky equation solver, which is GPUE. So for today, let's just go ahead and start talking about how we simulate this superfluid. Essentially, we follow what's known as the Gross-Pdevsky equation, which is IH bar d psi over dt is going to be equal to p squared over 2m plus v naught plus g psi squared plus, we'll do it minus, oh no, this is the whole equation, sorry. This is the whole equation right here. So we have a momentum term, and then two terms that are in real space, one of which corresponds to the trap, and another which corresponds to the overall interaction between atoms and other atoms in the system. So the idea here is that you have basically a bosonic system. You cool these bosons down to near absolute 0 Kelvin, and when you cool them down to this state, the bosons basically act as one giant macroscopic particle, all of which are interacting, and this is that interaction term. Now, in particular, we add an additional element to this term up here. So it's P, I think it's minus MA, I'm not sure if it's minus or plus, honestly, here. This here is a geometric gauge field, usually represented by Barry's connection or something like that. So based on like the underlying, I guess you could say atomic distribution, like based on the underlying kind of electric field or something you have in the system, if it's tuned correctly or something like that, you can actually impose a rotational effect on the system. And this rotational effect could be like, a standard laser rotation. So you're rotating it like you'd rotate, any type of water in a spoon or with a spoon or something like that. You can basically create any type of rotation or any type of rotational effects that you want, thereby creating any type of vortex structure you want just by modulating this gauge field term here. So what we have here is a system that allows for us to simulate basic Schrodinger equation, that's this guy right here, Schrodinger equation or for Bose-Einstein condensation, which would be a superfluid, which is the blue, and then basically an additional term here which allows for us to create vortices. And this is kind of where we're at, right? So we have components in real space, components in momentum space, rather components in position space and components in momentum space. A component that corresponds to the interaction between all of the particles, and finally a component that corresponds to the angular momentum or gauge field that we're reading into the system. That's what we have. These terms are all related to the general motion of superfluid systems, particularly Bose-Einstein condensates, which are quantum. Now, this is kind of rough, the way I introduced this, kind of hand-wavy, and I did that simply because we've talked about this before, and I don't feel we need to talk about so much more here. We'll answer questions as we get them. So we'll pop this up over here and pop that over there. So what I'm going to do next is I'm going to cd into projects and then GPUE, and I'm going to do a git pull origin energy fix to pull the latest changes. Okay, let's grab these changes. Okay, so now I'm going to cd into the Python directory, commit your changes, now I'm going to stash them. Okay, now we're going to git pull origin energy fix, grab the latest changes, and again guys, just ask me questions as you have them. I'm more than willing to discuss them as we see them. cd py. So I'm going to run the last Python code, which is this one right here, and I'm going to show you basically what's happening. So this over here, this is an initial guess that we put into the system for our superfluid Bose-Einstein condensate. We assumed that initially it's going to be some sort of 2D Gaussian, right? Then what we did is we moved the simulation forward in imaginary time, which is just a way for us to find the ground state of the system. It's a purely, I guess you could say, numerical construct, or I guess mathematical construct that we're using in order to find the ground state of the system. So you move it forward with time, you see that the Bose-Einstein condensate gets bigger and bigger, and at some point, we start to see these vortices form in the Bose-Einstein condensate. So these are all, again, little tornadoes that are piercing our condensate from the top to bottom. Again, vortices must either end at the edge of the condensate or reconnect in the form of vortex rings, but that's kind of beside the point. The point is here, we see these vortices forming, and eventually they're going to form a vortex lattice, like they're trying to form the lowest energy ground state of the system, and that's what we're looking for here. It's not there yet, but it will be there in probably another 100,000 time steps or something like that. Okay, so if we kept running it further and further, we'd get closer and closer to the ground state. The point is, yesterday, we were trying to do an energy calculation for that system. We were trying to find the energy, and like I said just a second ago, there are 4 components here that we have to deal with. We have the momentum space term, the real space term, the interaction term, and the angular momentum term. And for some reason, the angular momentum term was always wrong, and we couldn't figure out exactly why. Well, as of yesterday afternoon, while I was working on this a bit more, we managed to get the energy that was spit out directly from GPUE to match the energy that we had in our Julia script. So this basically means that now the energy is correct that's coming out of GPUE, and it is probably correct that's coming out of the script. What I need to do today is write basically a unit test. It's more or less just a test. It's not really a unit test here because it's kind of hard to do individual tests to the functions, but we want to do a test to make sure that the energy of a Bose-Einstein condensate with a single vortex is the correct energy for 2 and 3 dimensions. Now, you could say, oh, why don't you do it for 1 dimension too? And the reason we don't do it for 1 dimension is because a 1-dimensional vortex is kind of a weird thing. It's something known as a soliton. If anything, and it's kind of like a sound wave in the system. It's hard to really identify what a vortex of 1 dimension looks like. So that is, that's kind of where we're at there. Okay, so again, if you guys have questions, comments, concerns, anything like that, please feel free to let me know. Depending on how you guys are feeling, we may make this a short stream. It might be a long stream. I'm not really sure how it's going to go. More or less, I'm just trying to do research in a very open way. And admittedly, this is a bit complex and complicated. In some ways, I kind of feel like the only reason people want to watch this stream is because it's a bunch of technobabble. So, just feel free to just say anything you want in chat. Ask questions and that kind of stuff. Yesterday was quite good, but I don't expect that today we will replicate what, I guess, the popularity we had yesterday. I mean, yesterday we were regularly at 30 consistent viewers, and I don't think we'll hit that today. But we'll see how it goes. Okay, so we have this Python code. Let's cd back a directory, and let's cd into Julia. I'm going to go into vi-calc-energy.jl, and I'm going to modify this calculate range function so that it works for our system that we have here. 256, 1e to the -6. Actually, this should work, I think, right out of the box. Yeah, I think these are the right variables to use here. So I guess what I'm going to do is I'm going to write and quit, and I'm just going to run this calculate range function. So I'm going to run Julia calculate energy. I've modified the script slightly so that it outputs more than just the energy, the overall energy of the system. So now it outputs each individual component of the energy along with the total energy. And you'll see here that we have the kinetic energy term, which is 1.34 times 10 to the -33, a potential energy term, which is 5 times 10 to the -33. Then we have an internal energy term. This is the interaction term. This is going to be 3.779 times 10 to the -33. And then finally, an angular momentum energy, which is the energy of kind of like the rotation effect that creates our vortex. And that's going to be an angular momentum of 2.104 times 10 to the -33. Now, I'm particularly interested in figuring out what the energy of an individual vortex is, like what one vortex energy looks like. Didn't get a notification. I put a notification on Discord, I believe. Let me check real quick just to make sure I did. Yeah, I certainly did. Sorry that you didn't get a notification, but I'm glad you're here, man. So again, we're just continuing the superfluid energy system that we were working on yesterday. Again, we're seeing how these kind of open research talks go. We'll see if a research stream of this nature is worth doing in this way. And it's kind of one of those things, I'm not convinced this is the most optimal way to do this type of research. But on the other hand, I am convinced that we need to be more open with the research that we're doing. So I've got 2 different ways in which I kind of want to do this. I'm debating whether we need to keep doing the open research streams or just I need to start making videos on the research when they're published. We're kind of 50-50, or I'm kind of 50-50 on what the best thing to do here. So again, if you appreciate these streams and you like these streams a lot, specifically the research streams, let me know, because I'm very interested in hearing your guys' opinion, specifically the opinion of, like, how this compares to other content on Twitch. Like we had a discussion yesterday about how, programming channels on Twitch tend to have way fewer viewers than, a lot of gaming channels on Twitch. And you can never really reach the popularity of gaming channels with, programming channels. And there was a question as to why that is and all that kind of stuff. And I think there's just so much arcane technical knowledge with this type of stream that I don't know how possible it is to do this for like the long term. So this is kind of a general discussion I'd be more than willing to have. Live code from Visual Studio? Yeah, I'm definitely not using Visual Studio. There's no question. I can't use it. It's a pain. I mean, I guess I could try, but it's okay. But how would live code actually benefit? So everyone can pull it up simultaneously in general. Oh yeah, I could see that being useful. We could create in general, this particular system is going to be hard to work with because this is a kind of large-scale code base that I've been writing for the past few years. So it's going to be next to impossible for people like just to pull it up and just work with it. But for everyday stuff like just stuff that I'm doing on my 5 to 7 stream, yeah, I could see that being quite useful. So, okay, so I'm going to go ahead and try to generate a single vortex in our simulation. So we're going to see new projects, GPUE. Now let's run history grep GPUE. Before we're running the following command, so GPUE x256, y256, g100,000, p100,000, this command here. Let me explain what we're doing here. So we're going to run this here. So this is GPUE -x -y, so we have a 256 by 256 for our resolution. We're going to run 10,000 steps in the ground state. And only one step in real-time evolution. We'll plot every 10 or every 1,000 time steps, so we'll just output data every 1,000 time steps. We're going to write out to file every single time we're plotting. We're going to run with an omega of 0.6, and we're going to run basically with 10 to the 5 particles using the gross PDSK equation with angular momentum with a kind of very large trap in the z direction, so we're kind of squashing it into a pancake. That's kind of what we're doing here, and then we're outputting the energy. So what I want to do this time is I'm going to run this same command, except in this case, what I'm going to do is I'm going to run with an angular momentum 0.3. This is just at the threshold where we should not be generating vortices. So I'm going to run this, and I'm going to hope to get a result out that has no vortices at the end. And then after I get that, I'm going to imprint a single vortex in the system, let it run for just a bit. And then after letting it run for a bit, I'm then going to go through and, actually, let me just go ahead and remove all the data. So remove data, I'm going to remove it all, and I'm going to plot this again. And I'm going to do quite a few more steps. So let's do this. Okay. So what I'm going to do is I'm going to get a large Bose-Einstein condensate without any vortex in it. I'm going to imprint a vortex, and it should be with an angular momentum of 0.3, or rather an angular rotation of 0.3. This single vortex in the system should be stable in the ground state after imprinting it. So I'm going to try this out, see how it goes, and hopefully this works out okay. So right now, again, we're just simulating the Bose-Einstein condensate. If you've got questions, comments, concerns, anything like that, just feel free to post it in chat. As far as emotes are concerned, I am genuinely wanting to create a VI emote, which looks something, let me go ahead and pull it up on Discord. Where is it? Here it is. Oh, I missed it. Here it is. On Discord, that looks something like maybe one of these guys or one of these guys. And the reason I want to do that is just because obviously I use VI, not Vim, and so I took the Vim logo and I removed the M, changed the background color and stuff like that. The problem is this Vim logo is under GPL, so I don't know what that means for the VI logo. It means that it also needs to be under GPL, but I don't know how you can put something that is an image under GPL. I've never really heard of something like that before. So let's go back to Pi. I'm just going to run the last Python plot command, which should be up here somewhere. And I'm just going to modify these guys. So it goes here and there. Okay, so let's see. Hopefully we don't see a vortex in the system. It should just stay here. And it basically does. Yep, great. Okay, wonderful. So now I'm going to go ahead and read this in as the loaded wave function. Did you figure out the correct energy function? Sorry, did not get to the last streams. Yeah, so we did figure out kind of what was wrong with the energy calculation. So now it's output correctly from the Julia script, and it's also output correctly from GPUE itself. So now what we're trying to do is create a quick test and see if we can get some sort of intuition as to what the energy of a single vortex looks like. There are two ASCII arts on the Vim logo. The second one seems nice. I don't think the emote would work but a bot command that prints out ASCII art would be nice. We do have a bot command that does that. Let's see, what do we have here? Vim logo, open. Oh, you're right. So we do have a bot that can print out ASCII art. Right now it just does cow say. So if we do cow say, hey, it should do, yeah, there you go. So we get cow say, hey. It's actually quite nice. Buttercake made it. It's wonderful. Does it have the, let me see something. Can I do this? No, I can't. Okay, fair enough. So the cow say command has the ability to like make a stoned cow or something like that. So we're going to cd into data over here, and I'm going to cp wave function 0 const 100,000. I'm going to put this into wave function load. So I'm just putting this into a particular file so that we know we're going to load it into the next session. So wave function iLoad for the wave function imaginary load, and there. cd backend directory, and now we're going to read that into our simulation. So now our initial state is going to be the final state that we generated last time. What I'm going to do is I'm going to run this for actually real-time evolution for a few... Actually, maybe I should do ground state. Yeah, let's do ground state evolution, reading this in, but this time I'm going to run... oh, never mind. I know what I need to do. I need to run it in real time for just a few steps, and I'm going to imprint a single vortex into it. So we're going to do let's do 100 actually. That should be enough. And then we're going to print out every 100 here, something like this. And I'm going to imprint a single vortex into the system. Okay, a segmentation fault. Okay. Okay, nice. So what I'm going to do next is I'm going to go ahead and plot this guy. So we should be plotting, instead of wave function EV for the evolved wave function. And we're just going to plot 0 to 100 in steps of 100. So there's the, okay, that's not correct. Yeah, let's try this one more time. So I forgot a -r flag, so I forgot to read it in. Now let's try that again. So there's the read in wave function, and it doesn't have a vortex in it. Okay, let's check wave function EV phase. Which, you know, again, should wave function phase EV. I'm sorry, I need to fix this plot script. It's kind of crap. So here's nothing, and we should see still nothing. That's interesting. Okay, let's try this again. We did L1. Maybe there's something wrong with how I'm reading in these flags. Okay, EV, I think it's this one. Again, nothing. Nothing. Why are we seeing nothing? We should see something. Okay, well, let me just plot it for 10 time steps. And let me just do every one here. So let's see what happens. So what I should be doing is I should be imprinting a single vortex into the system, but for some reason it's not outputting correctly. So here I'm going to do 0 to 10 in steps of 1. Let's give that a go. So there's the initial one. Where is it? What? Where's our vortex? It's not there at all. Crap. Okay. Where is it? We should be imprinting a single vortex. SLZ100ER. What just happened? I was plotting the phase of the wave function. So if we have a 2π phase winding, let me just go to GPUE-group. GPUE-group. Here it is. Oh, that's actually not it. I need to go to the documentation here. And then we go to, let's see, what do we have here? GPUE functionality, vortex tracking. Basically, every time you see a 2π phase winding in the quantum phase, you know a vortex is there. So what I was trying to do was imprint a single vortex into the system. So just one vortex right there at the center. But for some reason, my imprinting function didn't imprint anything, and I'm not exactly sure why. So what I'm going to do instead is the following. I'm going to run, let's see, I'm going to run this guy that I ran before. Then I'm going to run a -L1, so to imprint a single vortex. And then I'm going to run this for what looks to be 10,001 steps. Yep, okay, so we'll give this guy a go. So this means I'm running it in imaginary time for a bit, finding the ground state. Then I should be imprinting a single vortex, and hopefully at the end of all of this, we see one vortex in our system that we can use for our simulations. If not, I need to figure out what's going on and why it's not generating the right state. because I have no idea why the phase imprinting wouldn't be working here. We've been using it for previous simulations before. In fact, the simulations you saw yesterday when we had the 4 vortices in the system, and one of them was flipped, that was entirely done via phase imprinting. So it could be that I just didn't give it a charge. I'll look at it. I'll look at it again and see what happens. So if this doesn't work, I need to figure out what the problem would be, which would be fun. It's a fun little adventure in physics land. I don't know what I'm saying. I'm sorry, guys. But again, guys, if you guys have questions, just ask, and I'll do my best to answer them as soon as I see them in chat. Oh, this is going to break, isn't it? Nah, it's fine if it breaks. So we're going to do wave function EV phase, and we're going to go from 0 to 10,000 in steps of 10,000. That should work. Wave function phase EV, I think is what it is. Phase underscore EV. So there's the phase. Oh, what? What are we looking at here? Okay. Yeah, I have no idea what we're looking at here. Let me try. So what I was expecting to see was something that looks like this. For some reason, the phase is like wrapping around like this in some sort of disc shape. So let me plot just the evolved wave function and see what that looks like. So here's that. I have no idea what I'm looking at. Crap. Okay. So, I have no idea what's happening here. I don't know why this isn't working. So I'm going to try the previous simulation that I had before. I'm going to run E of 10,000, plotting every 10,000. And what I'm going to do is try just imprinting a single vortex just to make sure I get the same result. And then if I get the same result, then we know that we can just read in the wave function without any problems. There's that guy. Yeah, there's that guy. So we get the same result, which means we don't have to redo the ground state simulation every time. But I have no idea. Let me just look at this one more time. I have no idea what I'm looking at here. Yeah, I have absolutely no idea what I'm looking at. I'm going to try imprinting multiple. I'm going to try imprinting multiple vortices, and just to see what happens, because I know it usually works. Let me try doing Q, 1, and let's just see what happens. So Q is the charge of the vortex that we're imprinting, and I'm just imprinting one singly charged vortex there. So we're going to do Python plot, and give this guy a second. Yeah, that's the same. So now I'm going to try Q minus 1. Okay, and we're just going to see what happens. Again, we just flip the vortex. Now it's going to be rotating the other way. A new phase of matter. It's not really a new phase of matter. It's a new phase of crappy simulations. Okay, that didn't help me either. I have no idea what I'm looking at then. Okay, let's look at it one more time. Then there has to be something wrong with how I'm imprinting a vortex. So I'm going to try to imprint multiple vortices here. I'm just going to imprint L4. Let's imprint L4. Okay, give this guy a go. And we'll see how it goes. Come on, dog. Do your thing. It's taking... I thought it was taking longer, but it wasn't. I'm just... This plot doesn't make any sense to me. So I'm going to plot multiple things and see what happens. So we're going to plot every 1,000. And we're just going to see what happens as we kind of move through this, see how the phases are changing, and see what we got. So there's the initial wave function. Ooh, hello there, my friend. What am I looking at? Jesus. I'm sorry, I didn't take the Lord's name in vain. Forgive me there. Yeah, okay. Well, if you're looking for some psychedelic photos, I mean, I got you covered, man. Am I somehow... I feel like the phase that I'm imprinting is somehow circular, like this. We need this as a follower subscribe animation. I could very easily turn it into a subscribe animation if we wanted to, but I just feel like it's not good enough for that. Oh man, what are we doing? Huh. Okay, I have no idea what we're looking at. So I guess I'm gonna... Why would the L4 not work? Let me try changing that to L1, and let's see how that changes. What's up, man? How are you? I hope you're having a wonderful day. Silja Russell, thank you so much for coming in. Okay, let me go ahead and F5 here. I got a message I have to respond to real quick. Good. So, one of the, how do I put that? One of the people, so this video that just came up from Minute Earth, like we're kind of monitoring the viewership and we're trying to see whether it's worth doing another sponsorship of this type. So, you know, someone just mentioned that it's doing pretty well. Let's see what this looks like. It looks the same, which I don't know what to think of. Oh no, it looks quite different actually. There's some time steps that are a bit different. I don't know what to think about this. Just say still, most people do, and doing good, thank you. Yeah, cool, I'm glad to hear that. Jerry, maybe we should check if a program is working, if the parameters are correct, by putting two of what, and see what happens. What do you mean, two of what? Okay, so that phase is incorrect. Let me check to see what's happening with the density of the wave function as we're going through. So I'm just gonna plot that. Wave function EV. Yeah, that phase is incorrect though, so we're not even putting the right phase into the system. Which means we are... I don't see any difference in the density. This all looks the same. So I don't think there's anything wrong with that. 2 vortices? Yeah, I just tried that. So actually I imprinted 4 vortices. So this L4 means that I'm imprinting 4 vortices. And then I tried imprinting just 1 vortex to see if there was a difference. And it just seems like it's not doing what it needs to do. So the implementation of the phase imprinting seems to be wrong then. But it's weird that it's wrong because I haven't touched that in forever. So I don't exactly know what the problem would be here. So let's see, let me check this command real quick. We have, let me just run GPUE-H and see if I forgot something. So this is the help command. I mean, we'll see what happens. So we have rotation, we're reading in rotation. Set flag to graph, that's deprecated, we don't use that. Box size, we don't worry about that. Device, coordinates, offset for the kill flag. Data, perform energy calculation, E-steps, unwrite right to file flag, help menu, param.csv, CFG, J, yeah, I'm not sure. Set threshold multiplier for easier void. I don't even know what that means. I need to fix that, whatever that is. I have no idea what it's doing. Let's see, K, L, yeah, L is vortex winding, 2 pi L. Set angular momentum flag to use angular momentum. Set 2D mask for vortex tracking. I think that would have been it. If anything, it has to be that L flag. Ramping factor, wave function, DT omega Z. Okay, so let me check this implementation of the phase imprinting and see what we have here. Because maybe I just screwed up with the phase imprinting when we were messing around. So a while ago, I messed up or modified how we basically put parameters into the system. So basically, when we initialize parameters, we need to make sure that they are initialized on the GPU instead of on the CPU and then transferred to the GPU. And so I did all the initialization on the GPU, and when doing this, I may have screwed up like maybe the phase imprinting or something like that. So I'm going to check this implementation to see if there's something wrong going on there, but I swear this should work. I don't understand why it wouldn't. Let me try increasing this omega real quick. I'm going to increase it to 0.6. I'm going to run the same code, see if anything else has changed. It probably shouldn't, but you know, just in case. Let's go ahead and run this. There. Yeah, so it's not doing anything. Crap. That means there is definitely something wrong with the phase imprinting. Okay, let me check the phase too, just to make sure. I think it's phase EV. I always get these mixed up. Okay, there's the phase. Yeah, this is the same plot we were seeing before, just slightly modified, but ultimately the same thing. Well, dag nabbit. That didn't work out, did it? Okay, so let's go ahead and try to figure out the phase imprinting stuff, because clearly there's a bug with this. I mean, or rather, there is something wrong with this imprinting. I don't know what it is, but there is something wrong with it. So let's take a look at what we have here. So I'm going to go ahead and go into VI, let's go back a directory. And let's go into VI source, and we're just going to go into parser.cu. I'm going to look for the -L flag, 1 second, and see what we're reading in here. So we read in winding. Here, the winding is set to be 0. Okay. So now let's go ahead and see where we use that winding. There's a VI init, VI source init, and let's look for winding. So the winding is basically the number of 2 pi circulations you have around your vortex. So the idea is if we want 2 vortices, we basically imprint a 2 pi or a 4 pi phase winding. So there's 2 pi circulations around where we want the vortex to be. So there we have the winding. It doesn't look like I'm doing anything else with that winding. Oh, that's because, oh my gosh. The person who wrote the code to begin with changed it so that this double L meant winding. So I'm actually going to just fix that. I'm going to call this winding all the time because I hate that. So let's go ahead and make this over here. And we're just going to grab all the errors and fix it. Oh, let's go ahead and control C here. CMake dot. And now let's make it. Because for some reason that was using the old school make file, which is fine. It works. But, you know, I prefer using the CMake version when possible. It's a bit more robust. Okay, let's see what we got here. Man. Okay, so let me also check Twitter real quick. What do we have here? Scroll down a bit. Okay. So it looks to me like for the Twitter votes, it looks like we're actually 50-50 between scientific software development and just doing a video on all of my research. No, that couldn't have worked. Let me try rewriting this. Let's go over here. Let's try making it one more time. It should break. Otherwise, there's no reason to have L. Oh, man. So I can just delete this variable entirely, and it doesn't matter. Crap, what am I doing then? Phase? So we want to imprint a phase. Here's a phase. If we want to read in a wave function, we may also need to imprint a phase. This will be done in the init2D and init3D functions. We have init2D and init3D functions in it. I thought it was just a general case init function. Well, dagnabbit. So I think I just failed, or I had forgotten to put in the phase winding step entirely when I modified the initialization function here. So let's see what happens if we run this guy, the same guy we were running before, but without this L factor, no L factor whatsoever. And we're just going to run that in real time, and we're going to see what happens. So we're going to cd in a pi, and we're going to plot that. There it is. Crap. Ah, dagnabbit. Okay, so a while ago then, when I implemented the phase imprinting, I literally didn't even put the phase imprinting in this version of GPUE. Crap, what happened? Why did that happen? Maybe what happened was it was in the init2D function, and then when I combined the two initialization functions, I removed the phase imprinting from the 3D version, because the phase imprinting was something that was hard to do in 3D, if I remember correctly. Well, that's a huge oversight on my part. Let's go ahead and take a look at how we can fix this. Dang, I mean, it would be fine if it was like a deprecated feature, but it's certainly not a deprecated feature. It's something that should definitely be in GPUE. So I'm gonna have to, I really need to add this in there. This wasn't exactly what I was intending to do today, but that's okay, you know? Sometimes research is like that. You intend to do one thing and you do something else entirely. So we're gonna see if we go back a directory. I'm gonna just go to the GPUE directory on GitHub real quick. So here it is, the GPUE repo. And I'm gonna go into actually probably the initial fork from the guy who developed this to begin with. I'm going to look at his phase imprinting implementation. So we have source here, and his is way different. He's got a splitop.cu file here, and we should have a phase somewhere in here. Phase winding. Okay. WC phase winding. I think that's the only time he sees it. Okay, so where does he initialize the variables? They should be initialized up here or something? So let me know what you guys think about the stream, if it's worth doing or not. I just kind of feel like maybe it's not as worth doing as I was hoping it would be. Okay, so... Oh yeah, he also made it so the winding... Bah, this is such a pain in the butt. Okay, so I need to figure out how to do this 2 pi phase winding. It should be relatively straightforward, so let me see where he put in this apply phase guy. So here we have the phase, and it says phase winding, wave function phase winding. So let's just move over a bit. Yep, of course that's the case. So basically it says he has phi, the winding, x, y, z, x, y, d, dx, dy, the lattice, get vortex UID. Oh, this is such a pain, isn't it? But I have the ability to imprint a phase. I know I do. Huh. Okay, so let's take a look at what we have then. I'm going to, going to take a look at what we have. So I have this flag in here. Let's go to vi source parser.cu. So I've got a flag in here, which is basically to check to see like which vortex we want to kill or which vortex we want to flip. So let's see, where is that one? I think it's going to be the J flag. Double threshold, threshold given as, oh no, it's not. Okay, so then maybe we're looking for the Q flag. Let's look for the Q flag in here. Here's the Q flag, imprinting vortex with charge Q. Yep, so it should be flip, true, charge. Yep, okay. So now we're going to go to VI source, and I guess it's going to be in it. Let's look for flip. Okay, so now let's look for VI source evolve, and we're going to look for flip. Boolean flip, apply gauge, if flip. Okay, cool. So we have apply gauge, if flip, which means, this is a different flip, isn't it? Because I'm so bad at this. Okay, you're right, that's a different flip entirely. And there is no flip in here. So let's go ahead and search for this. I'm going to cd into source, and now we're going to do grep -rln flip and see what we got here. And actually, I'm going to do flip. Okay, so let's go to vi source, and we're going to look for, it's not anywhere. Source evolution. Crap. So whatever I did, I accidentally deleted the ability to choose a specific vortex in our system and flip it. I accidentally got rid of that functionality entirely. Well, okay. I screwed up big time. .cu, let's look for flip. So we have flip false, and we have charge here. So let's look for charge. Yeah, we have charge there. So let's just do grep -rln charge. Evolution, let's see where it is. VI source, actually VI evolution. And let's look for charge. There, so in charge. Aha, okay, so we have kill it, charge. Okay, so it is used here. If we're planning to, best way to optimize is just to remove all the functions. Yeah, that's apparently what I did. Oh well, so we're gonna go here. And also, like, man, this whole thing needs to be reworked. I don't like this whole, all the 2D vortex stuff really needs to be reworked in GPUE. It's such a pain in the butt. Yeah, it's a huge pain in the butt. Is it raining outside? Oh, no, there's just a, some guy mowing the lawn outside. That's fair. Okay. So we have the ability to imprint a charge. So let's see, I'm gonna look into this. Oh, I see, it's auto kill it. And then we have wave function phase winding. Okay, I see. So what I need to do is look into this wave function phase winding function and see what we have here. So let's go ahead and go into grep -rln, and we're gonna look for phase winding, evolution manip vi source, and we're gonna go to manip.cu. Okay. Wait, where's the phase winding in this file? There is none. Why did you tell me there was, grep? Oh, I see why. Now let's go into phase winding. So here it is here. It says for, okay, so it basically goes through this as a sort of 2D space. So it says for II, oh my gosh, why II? Oh my gosh. I really hate people who use MATLAB so much. They just decide to go against like standard programming principles because they're like, oh, you know, MATLAB, I is imaginary or J is imaginary. It's like, come on, just screw you, man. Like that's only in MATLAB. I mean, I guess maybe in Python too, but still, it's just. Okay, so for I less than dim, we're gonna do fmod of winding atan 2 of yjj minus position dim over 2. Yep, times dx. So let's see, how are we going to do this then? Is there an fmod function available in CUDA? I think there is. It's just a floating modulus, right? So there should be an fmod of the winding times atan 2 of yjj minus position minus dimension over 2 plus 1. So I guess what we should do is we should implement a feature that allows for us to basically do this operation on any wave function that we're reading in, right? So we'll have the wave function initialized, and then after it's initialized, we then imprint a vortex. So that's what we need to do. I know this was in previous iterations of the code, but I'm not exactly sure where it would be. So I'm going to go and look and see what we have here. Let me go to commits, and I'm just going to scroll down and see, because I know I just deleted it somehow. So let me just look for init. Whew, can I search the commits? This is going to be hard to find. This is certainly going to be hard to find. Older. Maybe I can just grep the log? Preparing paper. Oh, I see. Removing unnecessary components and fixing a few warnings. Fixing unit tests, modifications to README. Fixing 1D case. More small-scale changes to unit tests. Freeing variables. Okay, nice. Adding changes to parse sum and energy test. Energy still incorrect. Removing DX parameter. Adding small-scale changes to ring operator. How long ago was this? 2018, July? Would that be correct? Did I do this almost a year ago? Could be. I honestly don't know, because I have no idea where I would find this. Okay. But what I'm looking for is the time in which I modified it so we had only one. Let me take a look at this guy over here. So I'll just mess around with it a bit. So we're going to go to view browse files over here, and then we're just going to go into source. And I'm going to take a look at init.cu and see if we have an init2d and init3d function. No, it's just one single init function. Okay, so this has been done a long time ago. Adding JBus, adding GPUE AST evaluation. Let's again go to browse files. Go back. Go back. Okay, and let's go ahead and go through source and check init over here. Oh, I can't believe. Yeah, this is still back when we had only a single initialization function. Well, crap. I'm going to have to go way, way back. Way back. And I'm just going to click on something at random over here. Finishing backwards ramp. Let's try this guy. Adding small scale changes to help file for TN10. That's nice. Let's go ahead and browse the files here. Hopefully we can find what we're looking for. If we can't, I don't know what to do exactly. Init.cu, init2d. Yes, so we have an init2d. So what I'm going to look for here is a winding. So we have par L winding. Okay, great. The issue is that we saved this as double L, which is a bit of a pain. So I guess I'm just going to look for all L's in the system. So Control F L. So this was, unfortunately, you can click the file and click history. Oh, I guess I could have done that. I didn't though. I should have. So we're just going to, yeah, of course there's more than 1,000 matches because there's a whole bunch of L's in the system. The problem is that like the person who wrote this code initially just decided that he'd have angular momentum as L, which is fine, I suppose, because physically it is kind of L for angular momentum. But the problem is that like single character variable names are just always a bad idea. I mean, I don't know. I just got a notification and I don't know why there was a sound to that actually, but let's see, what do we have here? Oh, Film Tire, thank you so much for the 100 bits. Really appreciate it. I hope you guys got a notification for that, by the way. I don't know if you did or didn't. For some reason, I wasn't expecting to get a notification, though, so I think that's a bit weird. Let me just go over here to Streamlabs real quick. Or I shouldn't have heard a sound for that notification, is what I'm saying. Let's go here. I'm going to check some stuff real quick. Can you check for a space L? I might be able to. Give me just a second, because I guess it would have to be L comma, maybe? Okay, I'll take a look for it in just a second. Let me go to, I was going to turn down the volume of the alert box over there. Let's see, widgets probably. Alert box. No, don't care. And let's see, so for bits. Oh, oops, I sent an alert to myself. I'm so sorry. I'm sorry, I guess you guys just saw that. Oh, okay, interesting. Weird. So I don't have anything for bits. I don't know how we saw something for bits there. I'm sorry about that. Anyway, thanks so much for the bits. I really appreciate it, Film Tire. I really appreciate it. I was just going to turn down the sound. Thanks a lot for the bits. I really appreciate it. I'll try to figure out those notifications later. I really appreciate the support. You're great. Keep up the good work. The research is going well. Thanks for asking. I'm so sorry. I didn't mean to sound like ungrateful there. I was just saying we're trying to figure stuff out. And so I didn't know if the sounds were annoying to people or not. Trick, can you check for space L space? I sure can. L space, needed for later, winding L, function loaded, later. Okay, let's try L space over here. L, 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 L. Okay, let's try L comma. Nope. Crap. I have no idea where this is. But it's here somewhere. I don't know where it would be though. So it's going to be in the init2D function. So let's just pop up to the start. Here. Init 3D. It's certainly not there. It's going to be in here somewhere. Let me see if there's a winding. No, there wasn't a winding. We just looked for a winding. Wave function over sum. No, that's just summing them all together. Write file. Oh, it must be in here. This is where we defined all of the wave function and stuff. No, actually, is it an init or would it be in the evolve function? Wave function. That seems fine. Dimensionless. Part of b-value equals unit test. Let's see, dimensionless. No, I don't even have that one working. Wave function. Sum plus equals square root. I guess maybe L times? Oh, here we are. There we are, phi. So we create a phi, and then we basically put this phi onto the system. That's what I'm looking for. Fantastic. We're getting there. I do feel really bad. Sorry, Film Tired. I feel like really bad. I'm kind of low energy right now. So I apologize that I sounded kind of mean or rude or anything like that if I did. Okay, so L star, Atan, we have 2 pi. Great. So this is what I'm looking for here. So this is the phi. Now let's see what we do with the phi. We say wave function is set the wave function, and we're reading the phi into our wave function in there. So what I'm going to look for now is our operators, and I'm going to see how we're currently initializing our wave function. VI source, actually VI operators. And let's see what we got here. I'm going to look for, we have the Laplacian. We created the Laplacian before. So now I'm going to look for it to see if we have any phis in here. We do have a phi, and we're storing a phi. But it looks like we're not initializing a phi. Oh, we are. Phi here. So we have CUDA free, phi GPU, CUDA memcopy, CUDA memcopy phi. Okay. Par wave function. So it looks like the wave function does actually read in a phi, but it looks like we're not initializing that phi correctly. Okay. So we have the phi here, we're mallocing it. Okay. And then we do phi GPU. We do phi GPU. So we need the phi. So we need this phase to work for our wave function. So like the function that's generating our wave function does read in a phi. That's good. The issue here is that I think the way I have this set is we can generate a phi, but I don't think we can imprint it. Well, let's just see what happens. So let's get this phi generated appropriately. So n CUDA memcopy phi GPU, wave function. If part of bval is wave function here, otherwise we create the wave function. Wave function here, phi GPU. Oh, I'm gonna have to take a look at these wave functions that we have. I know wave function sounds stupid, but I mean they're functions to generate the wave function, right? So what else was I gonna call them? Okay, so what do we have here? So we have the phi. Where do we generate this? It doesn't look like I do, right? Because here we have the phi there. So I malloc it there. And then I do that. So let's go to VI source and operators over here. And let me take a look for WFC. Generating wave function. Yeah, I don't know what I called it. Standard wave function. That's what I called it. So where's our phi? So fmod, oh, I generated here. The heck? So I say we have phi GID is fmod there. So that means I need to read in the winding here. But that means the winding isn't being read incorrectly. Or something. Has to be, right? Otherwise this doesn't make any sense. Well, let me try something else then. Let me try running this GPUE code. But let me try running the ground state evolution actually for a bit. So where's our ground state evolution with L1 in there? With an omega of 0. Well, let's just run it for 1,000 time steps here. And we're just gonna run that for 1 time step. And we're gonna plot every 1,000 time steps. Actually, no, let's just do 100 time steps. Plot every 10. Okay, so there's our GPUE. And it should be not reading in anything. I don't think so. I don't think we're using the -r command or anything. Okay, so let's plot this real quick. So we're going to quit there. We're going to cd back into the Python directory, and then we're going to run the last Python command here just to plot our wave function and see what we have. Okay, so we're going to plot every, I believe, 10 for 100. Oh! How interesting. Okay, that's quite interesting. The initial state had... I see. So when I modified it, what I did was I made it so that the... Okay. Well, let's try something else then. So I'm going to try changing this to an 3.5. Okay? And we're just going to plot this. There's the initial guy. Okay, that's super interesting. So this seems to mean, or this seems to be, that we are actually imprinting a phase on the initial wave function. But apparently, that phase is not it's not staying in the ground state of the system for some reason. So I'm just going to do Python plot. There it is, and now it's gone. But I don't understand. Oh, that's because I'm doing wave function. Oh ho, let's do wave function phase. It's wave function phase. There it is. There you are. Look at you. Look at you, my man. Look at that beautiful vortex in the center of our system. All right, nice. We got something. So let's see what happens if we just do wave function. Yeah, we got that vortex. Look at that vortex, man. All right. Admittedly, it is a bit small, but we have a vortex. Okay, so I understand what happened now. When I read in the phi, when I read in the L1, I wanted to read it into the ground state evolution, not the real-time evolution. And the reason I did that was because I didn't want you guys to be able to just imprint a random phase onto the wave function and then run it in real time, because that's just going to give you a whole bunch of like random, I don't know how to put this, it's just going to give you a whole bunch of like just crazy sound waves and stuff like that. So it's not going to be a good simulation. That's fair. Okay, I understand now. I know why I did that, and this is actually a better implementation, but I'm an idiot. So let me go ahead and decrease the number of atoms here to 10 to the 3, so we decrease it by 2 orders of magnitude. And we're going to run this for this number of steps. And we're going to see what happens. Okay, so how many times did I do that? Something like this, something like that. That might be too long. So while it's running, I hope you guys are having a wonderful day. Please talk about your life. I do understand that, like, again, there aren't too many people watching right now, which is, again, fair. The whole point in this particular stream is just to be open about the research that I'm doing and stuff like that. Okay, so 40,000. Let's go ahead and start plotting. So here's the initial guy. Ooh, that is a huge vortex, and it's gone. It is definitely gone. Let's close that. Stay over there. Okay, so I'm going to change to 10 to the 4. That vortex was too big. Okay, we got this guy. Let's go ahead and plot it there. So here's the initial wave function. Give it just a second to do the next step. Here. Okay, there's our vortex. I'm liking that vortex. Let's see if it stays. Okay, it doesn't want to stay. It's leaving. Which means we're not rotating fast enough for that to be the ground state. Okay, so let's do Control C over there. And let's rotate just a bit faster. Shut up. Okay, so we're going to do this at 4.5. Okay, and again, we're just going to rotate a bit faster. The idea here is that we generate a stable vortex in the system. I have an essay to correct for my classmate, and I always learn new ridiculous ways to organize paragraphs. Ha! Man, I know that feeling. Like, I have to edit a lot of papers every now and again for people. Well, not a lot of papers, but I have to do some editing. And it happens kind of frequently to me. So we have this guy. There's a single vortex. It's still leaving. Okay, why are you leaving then? Control C. Let's go here. So we have L1, L. Yeah, this should be fine. All right, we're going to try 5. I don't know why we have to rotate so quickly, though, to keep these vortices in the system. Because usually at an omega of 0.5, like it's a lot of rotation. So this seems like maybe too much rotation. There's our vortex. Why are you leaving? Okay. quit out there, quit out there. Try 0.6. This is really a lot of rotation though. On the other hand, like we're fairly confident that we have the correct energy. Ooh, okay, nope, the energy is also incorrect. Shoot. There's your vortex. It's gone. It's gone immediately. Control C. Why? Why is it leaving? Is it just because... Let me try increasing the number of particles one more time to 10 to the 5. And let's just see what happens here. So this is the same simulation we were running before. We should see a single vortex in the system to start, and then we should see, oh crap. Then we should see multiple vortices just appear. That's not what I wanted to open. This is what I wanted to open. Great. So we're going to CD in projects, GPUE, and then we're going to CD into GPUE, and then we're going to go into Pi. And now let's go into the last Python plot. Yes, here it is. There's our vortex. Yeah, that's what I was expecting. Crap. Control C over here. Control C over here. Okay, so we're going to drop this down again to 0.3. I think that vortex is just too small to really get a good understanding of this system. I mean, like, it's just too small because, like, yeah, that's too much. Okay. No, stop it. Stop it. It just keeps plotting. All right, so 0.3. Let's try 0.2. Again, I'm just trying to get the right balance for the rotation here, so that one vortex is definitely in the ground state. And then once we have that, we should be good to go. There we are. There's one vortex. Let's see if it leaves. And it doesn't. It seems to stay. Okay, cool. So this is probably ground state-esque, or ground state-ish. Yep, seems to stay there just fine. Keep going. Is it leaving? 1 second. It is certainly moving somewhere. I don't know where it's going, but it's certainly moving somewhere. Yeah, it's leaving. It's leaving condensate. Crap. Why did you do that? How did I even do that? Crap. Bring that over here. Okay, so let's do a quick Control C over there. Control C over here. I'm going to try 0.3 again, because I think last time I just wasn't plotting correctly. Because this should be about correct, I think. So let's go ahead and Python plot. Okay, there's the initial wave function. There's the first step. Give it a second. I'm going to let it go one more step before continuing. Okay, it's still there. Yeah, so we're just going to let this run for a bit and see if this vortex goes anywhere. And if it doesn't, it's already going somewhere, isn't it? Yeah, it looks like it is. It looks like it's moving over there to the left again. Yeah, it's trying to get out of the condensate. Ah, dag, nabbit. Okay, so we'll try it again. Nope. Okay, so we'll try it one more time with 3.5, maybe? The thing is, I know that a rotational frequency of 0.3 should be about correct, so I don't understand what exactly is going wrong here and why it's leaving the condensate. Yeah, I have absolutely no idea. So this is something I'm gonna have to look into. Okay, cool. Sorry, I was checking notifications on my side screen. Let me go ahead and move this over here. Okay, so let's go ahead and check these plots. Python, here, there's a single vortex. It's still there, it's moving, it's leaving. Why is it leaving? It's gone. You know what? I think I might know why. I think I know why. Control C here, and what I'm gonna do is I'm going to try changing the winding so it's in the opposite direction. I think I know why. I think I know why. I got it. I think I'm imprinting a vortex of the opposite direction of what I need. So I think it wants to leave because the vortex direction, like it wants to spin this way for the ground state. I'm spinning it this way, but I'm imprinting a vortex going the other way. And that's why it's leaving. Yeah, it has to be. Has to be that. All right, let's Control C here. So what I'm going to do is I'm going to modify the phi in our wave function. So let's go to VI source. Actually, VI observe. Nope. vi, go back a directory to source, and then we're going to go to, hey, Artem Gem, how are you, man? I hope you're having a wonderful day. And so we're going to go into source, and we're going to go into operators.cu, and we're going to look for phi underscore GPU. Here it is there. Now let's see. I think I'm just going to look for wave function. I think it's kernel wave function std for standard. I know this is a dumb name. Forgive me. Just forgive me. Wave function. Nope. 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 Where is it? I can't find it at all. Oh, come on. Here it is. K-standard wave function. So fmod here. I'm going to... fmod should be between 0 and 1, right? So this would mean... I'm going to put a negative here. Let's go over here. Let's make that. And then I'm going to quit out of this guy. And then I'm going to try running that. And we're going to plot this. Give it a second to plot, and we'll go from there. So here we have the standard wave function that we just put in. Then we have first time step. Come on. Second time step. Yep, looks good. Third time step. Okay. Good, good, good. So again, this is just because we were rotating that way, but we put a vortex in that was rotating the other way. So we had to put a negative in front of the phi. That's nice. We had a similar case when I was trying to figure this out for the 4-vortex simulation I was running not too long ago. I also ran into this error. And I ended up just rotating, like making it so we rotate the opposite direction to fix the problem. So this is actually probably a better solution, just putting a negative in front of the phi. Good. Okay, I'm happy with that. So now, oh, I need to, I canceled the wrong one. Let's let this run for the whole simulation. And then we'll plot it at the end. Okay, nice. So we're getting somewhere. So now we have the ability to get a single vortex in our quantum system. Cool. So now we have a single vortex. The question is, what do we do from here? So what I'm going to do is I'm going to check the energy that is output from this system. And the reason I want to do that is I want to see what the energy of a single vortex is. And if we can figure out what the energy of a single vortex is, what it means in terms of angular momentum, we can figure out like what one vortex means. And if we have 2 vortices, we can figure out what that means. Does that make sense? Like what I'm trying to do is figure out like what the energy is supposed to be for these quantized units of angular momentum. And then I can create a test where we can check to see, hey, if we have a single vortex in the system, what does that mean in terms of energy? And then we can do a check on the angular momentum energy and the other energies in the system. Okay? It said located 403 vortices. That's definitely incorrect. So let's go ahead and plot this guy for all 10 steps and see what we have. Amazing, film tire. Thanks, I guess. Okay, so here we have the system. Again, we see that single vortex in the center of the system. That's precisely what we want to see. Great. Okay, perfect. Okay, so now I'm going to plot the phase just to make sure there's no anomalous phases being created here. Phase, and let's just go ahead and say 100,000 here. Okay, so here we have the initial phase that we imprinted in, and there we see the phase of the wave function after a couple steps of imaginary time evolution. So this is most probably a very close approximation to the ground state of our system. A vortex doesn't hate us and leave it anymore. Yeah, I mean, it's fair enough. Like, we're working with it instead of against it. That's kind of what happened. But you're right. Why not make unit tests? That's what we're trying to do, Nick. So we're trying to make a unit test right here for the energy calculation. So what we're going to do is we're going to be testing. So what I need to do the test is I need to find the energy of a single unit of angular momentum. And if I can find the energy of a single unit of angular momentum, and we can definitely figure out, like, standardize this unit, then I can make a test for the energy calculation to make sure that the energy calculation is correct for 2 and 3D cases, which is what we're trying to do right now. Although I'm interested to see what you mean. So what other unit tests would you... so one unit test I should have had in there, but I didn't think about, was making sure the phase around here was correct. That was something that I just didn't think about. There's a lot of things in here that I just, the unit tests are based off of like does the simulation work correctly? Does it produce the right output for particular test cases and stuff like that? This is really the only way we can, or I know, to check to make sure a physical simulator is producing correct physical results, is to check it against what you know analytically it should produce. It's unfortunate, but that's the only way I know how to do it. Let me go ahead and get some water over here. Okay. Okay, so that's where we're at. We've got this wave function, we've got a single vortex in the wave function, and then we are going to be working with this vortex to find like function by function tests. Yeah, but what do you mean function? Like, what are we testing in each function? So we have a test for each kernel. In the unit test. Here, let me show you what we have. So let's go into cd back directory. Those system integration tests. Yeah, this is what we have. But we have a couple of different unit tests here. So let's go into vi source and unit test.cu. So this file it's not too long. It's only 1447 lines long. We could add more tests in here. And we do test to make sure that the output of each of the kernels are correct. And we check to make sure that the output of each of the initialization kernels are correct and all that kind of stuff. Like, we check that. The problem is we check it based on what the kernel is supposed to output. But then we also have to check to make sure that it's physically correct. And that's the issue, right? Everything that we're outputting is fine, with the exception of the 2D vortex stuff, which I'm having trouble working with. But every other thing in the system is correct. Hey, Fulter, how are you? Simule cow in the chat. Okay. So we have unit tests for each individual function, most functions, at least all of the GPU kernels we have unit tests for. The main problem is that we just don't know like what it's physically supposed to output. So like that test error is something that, wouldn't have been caught by a function by function unit test. It would have been caught like by an integration test or something like that, or a systems test or something. And that's kind of what we're working with right now. We're trying to basically we're going to create a test case such that we know the output is correct. Does that make sense? Like we're creating that one vortex case. And now that we have that, we can work with that as our test case moving forward. But again, I'm interested to hear what you say for like unit tests for other things, like how we could have done this with the unit test and stuff. Because I don't know any better way to test this, but there could be. I'm just a bad software developer, You found cow emotes? Let me take a look at those. Those are definitely cow emotes. Who has these emotes? Used long, used moo, used roar. I don't know who used is, but thanks for all the emotes, I guess. Again, as far as emotes are concerned, I'm probably going to make a VI emote. I'm looking into this, so we'll see how that goes. Okay, so we have this unit test. What I'm going to do, we're actually going to be working on this unit test in just a bit, or this unit test.cu in just a bit. So what I want to do now is check the energy of the system. So let's go ahead and cd into Julia, and we're going to look into the calc energy .jl. His name is Used Pizza. Oh, interesting. Why does he have cow emotes? Okay, so we have here this calculate range, and we're going to calculate a range from, I believe it was 10,000 here to 100,000. What do we have here? What ended up being the energy problem? The energy problem from yesterday was simply a factor of 2. So there was a factor of 2 in the interaction energy that I wasn't taking into account. So once we got or added in that factor of 2, the energies were of the right order. And so we had everything kind of right. We were just off by a factor of 2 for one of the energy calculations. Kind of embarrassing, but it happens sometimes. So let's go ahead and right quit, and we're just going to run julia calc energy.jl. And let's see what we got here. So what I'm hoping to see is that the angular momentum energy is always roughly the same, and it looks like it is, 2.315 at the start here, and the angular momentum energy after the first couple steps is 2.315. Okay, so now I'm going to run the same simulation again, but with a slightly smaller omega, so it's rotating slightly less, and I'm going to check to make sure that we're still in the ground state with this slightly smaller omega. So if we rotate slower, right, in an ordinary physical fluid, you'd expect like the vortex that you're creating to be slightly smaller. However, if so you called it. However, in this case, because these units of angular momentum, because they're units of angular momentum, they have to come in a quantized way. If we rotate slightly slower, we'll still just get the same angular momentum, or we should. I don't know exactly intuitively what this is going to give us for a number. Factor of 2 pi. Was it next to a pi? It was not next to a pi. It was next to a g term. I totally said you either had an extra or were missing a 2 pi. You said You said 2 pi, but we were not missing a 2 pi. We were missing a factor of 2 in the g psi squared term. So it wasn't close to a pi at all, but it was 2. It was a factor of 2. I will give you that. Okay, so let's give this guy a go. I'm going to go ahead and plot this with the Python script one more time. Actually, let's run the energies first, since I'm already in this directory. juliacalcenergy.jl, and let's see what the energy is at the end here. 1.98 times 10 to the minus 34. So let's see what it was up here before. It was, looks like 2.37, 2.31 times 10 to the minus 34. And now it's 1.98 times 10 to the minus 34. I'm not sure the intuition here, because we are rotating faster. So in principle, this faster rotation up here, with the rotation of 0.35, should have a higher energy, no doubt, because a single vortex is further away from the ground state with a higher rotation than it is with a lower rotation. Does that make sense? So if you're rotating really fast, you want more vortices, right? So if you're rotating really slow, and you only have one vortex, that's probably okay, because if you rotate faster, you probably want more vortices. So I guess intuitively this makes sense, but I don't know how to create an energy test from this. Again, the hope is that we're going to be able to create a test to make sure that the energy calculations are correct for 2 and 3D, right? And so just to reiterate our point here, new page before, we have multiple different energy calculations. We have a momentum energy calculation. So we have momentum, position. We have the interaction term. And then we have the angular momentum. These two guys can be tested relatively straightforwardly just by checking the energy out of a simple harmonic oscillator, right? So we put the quantum system into a trap. It's a simple harmonic oscillator trap. And we know what the energy of the ground state of this system should be. So we run it in imaginary time. We get the basically Gaussian out at the end. And we know what that energy is. So we can check these guys because these guys are in the basic Schrodinger equation, right? So IH bar d psi over dt equals, I guess it's going to be p squared over 2m plus v naught. Now these are the terms we're having trouble with. The interaction term, which is the g psi squared here, and then the angular momentum term here, minus omega lz. Okay, let me try redrawing both of those. Omega, one second, omega lz. Okay, so these are the two problems we're having there. So with the red term and the blue term. Jerry, thank you so much for coming on. Have a wonderful evening. Good night. And for anyone who might be going to sleep because it's, you're somewhere in Europe and it's super late your time, please just go to bed. Don't worry so much about it. I mean, I appreciate that you're here. No doubt I appreciate that you're here. But at the same time, I don't want you guys to stay up super late and then be grumpy in the morning because of this, Okay. I know no one's probably staying up because of this, but I'm just letting you know. If you need to go out, no problems. The only real way to test it is to do a physical experiment. Well, that's actually what we're doing, right? We are doing we're basically trying to find the ground state, the lowest energy state of the system, right? And so the lowest energy state has a vortex in it. Yeah. Let's go ahead and catch up on chat. Ralph, 124C_41, thank you so much for following. How do you think it's possible that some of unsolvable physics problems comes out from our not complete understanding of mathematics? For example, square root should return positive and negative answers, but by consensus we decide that only positive matters. In general, we use a range of principle for multi-valued functions, but who said that nature cares about our consensus? This is a good question. I would say that, especially for complex numbers, there's a good series out actually to understand complex numbers called Imaginary Numbers Are Real. Let me go ahead and look at that. Imaginary Numbers. I really like this series. It's a good series on YouTube. Helps you understand basically complex numbers and stuff like that. I definitely look into this. As far as the underlying question that you're asking here about how Blub 5, I'm staying up because of this. Well, I'm glad you're here. Thanks so much for being here. As far as the underlying question of how do we know, mathematically we should get out a positive and negative from a square root, right? But how do we know that only the positive matters? I don't know. I mean, this is something that we just know based on physical intuition, right? We know that mathematically, this particular formula should be giving us out this physical quantity, and we know this physical quantity doesn't, this physical quantity can't be negative, you know? Nature doesn't care about our consensus, honestly. I would argue it's almost, yeah, it is that way, right? So mathematics, at least in physics, math is a way to observe, math is a way to model the world around us, right? And so if mathematics is not appropriately modeling the world around us, then it's not doing its job, right? So, I mean, I agree with you in saying that a lot of physics does kind of push the boundary of mathematics in some ways, especially nowadays string theory is doing this. And I also agree with you that a lot of math can't immediately be applied to a lot of physical results. I agree with both of these statements. I don't know how this applies to some unsolvable physics problems, though. I kind of need some more information on that as to what you mean by that. Single Mingle 21, thank you so much for following. Really appreciate it. Okay. So I'm going to pause here for just a second for questions and anything like that if you guys have any at this point. Again, we've been able to generate a single vortex in our system. We found a bug in the code, which basically made it so when we imprint a phase, it's imprinted in the wrong direction. We have it imprinted in the right way. May I link a video that you found enlightening? Please do. So now we know that there was a bug in the code. We know that we can get the vortices to rotate in the correct direction now. Now we're going to try to figure out how to set up these tests. And that's something I'm not so sure how to do. One other thing I'm going to have to look into is how to do this in 3D, right? So the 2D stuff that we've been showing is fine, but to do this in 3D, it's going to be a bit of a pain. So I'm going to have to try to figure out how to do this in 3D. In principle, it should be basically the same thing. But again, here's the problem. For the energy calculations, we can very easily find the energy of a simple harmonic oscillator. So we can check these two terms. Anything that's in the basic Schrodinger equation, we can check. In principle, I've got a feeling I can find some analytical value for the ground state of a Bose-Einstein condensate. So we can probably also find some sort of quick test for this here. But I don't know, at least I haven't been able to find, and this was via frantic Google searching, admittedly, I don't know a good value to put on this angular momentum term. So I was going to try to do my best to figure out how to create a test, how to figure out what the energy of this angular momentum term is supposed to be. And again, these are just different constituent components of the wave function. We have like the velocity component, the component of the trap itself, the component of the interaction between all the particles, and then finally we have the rotation term. And this rotation term is the one I don't know how to check at all. A super cool channel. As a community college computer science student gearing up to transfer to university, it's cool to see what research looks like. Oh, cool. I'm glad you like this stuff. Oh, crap. Okay. I will not watch it here, but I'm glad you linked it. Let's see what we have here. Just because it's a bit long. Truth about Tice, Lambda Days. So I'll put this over here before my stream, so I just remember not to delete it. Yeah, so as far as this stream is concerned, what I'm trying to do is I'm trying to do all of my research in like a very open way. So I'm just trying to see how open we can make this research and see if we actually get stuff done. So far, I can say we get a good bit done during these streams, but it also comes at the cost of, I guess, the viewership. It comes at the cost, don't spill another smoothie. Oh, man. No, I didn't do that. I almost dropped my watch, though. I mean, this mouse works okay. Like, I have this guy, and then I also have this guy, and it works okay, but this guy double clicks, and this guy is annoying because, like, I have to keep putting it up in its well every time, you know? So I can't, like, keep my mouse at a particular location. They're both annoying, but it's okay. Like, I'm doing okay with it. I'm happy with this setup. I mean, I was happier with the trackball, but I'm happy with this setup. It's okay. Okay. So let me see if we can find the energy of a Bose-Einstein condensate. I'm just going to Google this real quick. Energy Bose-Einstein condensate. And again, guys, if you guys have questions about really anything, just ask them. As soon as I see them, I'll answer them. I'm quite interested in this vote, actually. This vote is incredibly interesting. So like I said before, I want to make a video on the research that I've been doing recently. And probably at the end of the video, I'll be highlighting that I'm doing this research live on Twitch, all that kind of stuff. Regardless, I want to highlight some of my research. And the thing is, I said, what research seems most interesting to you? Obviously, the most exciting one is all of the above because people want more videos. Fine, fair enough. What's interesting is these three. I was expecting superfluid vortex chaos to just literally just smack the other three options out of the water, because the other three options are GPU superfluid simulator, scientific software development, and superfluid vortex chaos. So I was expecting superfluid vortex chaos to just be like, yeah, that sounds amazing, like Folster said down here. But nah, people were like, scientific software development, let's talk about that. Which, admittedly, sounds like the least interesting of the three. But hey, I mean, it's up to you guys. I want to talk about all three of them. They're all really cool. I will probably do a discussion on all of the above. It was mainly a way for me to figure out, like, what we wanted to talk about first. You know, what we wanted to, like, how I wanted to phrase this stuff. So anyway, I thought that was kind of interesting. Just that, I don't know, that people are like, oh, let's talk about scientific software development. It's like, there's superfluid vortex chaos right there. Like, come on. Anyway, mostly I meant something like discovery of positron. Before that, there was a function that described electron, but it was working fine with negative value. But nobody cared because, LOL, there's no way such a thing exists until it was actually found. So what if there's another concept like that also exists, but we just ignore it, like imaginary time? What if it's real? So imaginary time, yeah, so I've mentioned imaginary time a lot with these streams. That's because to do the imaginary time evolution, we do something called a Wick rotation, which is basically means we move into imaginary time to do our simulation. And this allows us to find the ground state easier and various other things. You're right that imaginary time is not like a real quantity in that it is complex and it is by default imaginary. And I'm not really sure exactly how you'd interpret imaginary time physically, or if it has a physical interpretation at all. Let's see, what was I going to say here? But it's a very interesting thing to say. I think overall you're correct that, you know, our idea of physics is constantly changing as we learn more and more about the world around us. And nowadays people are really pushing to have a good understanding of like dark matter and dark energy and stuff like that. I mean, I'm doing research in my area, not necessarily with the hopes of discovering new physics here, but with the hopes of discovering new ways to interpret, you know, quantum turbulence and stuff like this. There's a lot of very good questions here that need to be asked. And a lot of them are kind of right at our doorstep, you know, like a lot of turbulence questions. It's super easy to find turbulence. So why don't we have a good understanding of it? Why can't we simulate it very well, you know? And these types of things, I mean, this is kind of the pushes of physics research, you know, trying to discover things that help us understand the world just slightly better. And you're right that we're going to find something real weird, I'm sure, in the near future. We'll find that dark energy somehow allows us to time travel. Well, I don't know, we'll find something. I don't know what it is, but we're going to find something at some point that's going to radically change the landscape of humanity, as it has for the past 500 years. Every time we discover something new, the world changes somehow. I don't know how, but it changes, eventually. You know, sure, it might take a while. And it's been more than 500 years. It's been, you know, thousands of years since you know, basically mathematicians existed, and they started, like, just changing the way people did carpentry, you know? We've slowly but surely just changed the world, just step by step. And that's kind of what's so interesting about research, right? Like, you're doing stuff that no one's ever done before. And admittedly, it's annoying, it's complex, it's hard to follow, but it's nice because you're doing something that no one's ever done before. And the research I'm doing here, people have done this. Finding the energy of a quantum system, people have done that. But a lot of the other stuff people haven't done, you know, like one of the papers I'm going to be working on, or I'm going to be publishing soon, is about a stable generation of quantum vortex rings in a Bose-Einstein condensate. So there's a lot of just like cool things that you can do that people haven't been able to do before. And sure, they're small steps, but eventually you get there. And I'm sorry that I'm rambling so much. Let's go back to Google searching, because that's what I'm known for. Energy of Bose-Einstein condensate. The thing is, every time I Google this, I don't find anything real, like really useful, you know? Like, sure, this is DuckDuckGo, let's try Google, but ultimately I don't find anything particularly useful when I do these searches. They say, you know, the energy's in the ground state, but it's like, well, what is the ground state? What does this term, what does this give us? That's the question. I'm not sure. Chapter 3, Bose-Einstein condensate of an ideal gas. I'm just gonna take a look at this and see if I can find stuff for energy. Energy, yes, I know this. I think I've been on this site before. Eigenenergy, energy single particle. Yeah, I don't know. I don't know if it's a function of n or not, you know? Like, maybe it is, maybe it's not. I have no idea. Let me go ahead and plot the previous guy that we just had, cdpi. Let's just run Python here, just to make sure we still have a single vortex in the system. Yep, we've got our vortex. It seems fine. No idea. This is the issue. Like, we're able to generate the state that I need, right? We have a BEC, we have a vortex in the BEC. This is the state I want to work with because I know I can very easily figure out what the energies are. But I have no way to know whether, like, I don't know how to relate this to a physical value. Does that make sense? Like, I need some sort of test where I can say, hey, analytically, this particular value should be this. So now let me check in my test to make sure it is this. Like, I don't know how to do this because I don't know what the value should be. So I might have to ask someone, like just ask someone who's better than I am at this. But the thing is, I just wrote a paper and we just submitted the revisions to a paper yesterday. And it seemed like, the people who should know this, being my boss and a very close collaborator that used to work in our unit, didn't really have a good intuition as to what the value should be either, really. Like, we understood the order of magnitude, no doubt. And we understood intuitively that the angular momentum should vary as a certain factor, depending on how many vortices you have in the system. But we didn't really have a good understanding of, or at least I didn't have a good understanding, and it didn't seem like they had a good understanding of what these values should be. Like, I know the energy of a simple harmonic oscillator, but I don't know the energy of a Bose-Einstein condensate with a vortex in it, so I can't check as easily. So maybe we're left in the unfortunate position where I don't have a good test for this type of thing. Maybe that's the case that we have. Maybe we don't have a good check for the energy. At the very least, we have an energy function that seems to be working for the cases that we've tried it on. So we know it works in 2D, we know it should work in 3D, we know it should be okay. But I don't know how to check, and this is the issue. So let me go ahead, what was I gonna do? We have this term, we have that term. We plotted everything, we have everything correctly. I guess I'm just gonna do some Google searching here. Oh, no, what I wanted to do is I wanted to run this with an L equals 2 instead of an L equals 1. And while this is running, I'm gonna be right back, guys. Sorry about that. Okay, I'm back. Sorry about that. The simulation is done, so let me go ahead and take a look at what it looks like. So we're going to plot this guy. Here's our 2pi phase winding. We still have 2 vortices in the system. So I'm going to plot this again, and we're just going to check to see what it looks like as we run it here. So we're going to do that and that, I believe. Okay, so here's the initial system. There's our system with 2 vortices, and it should just kind of stay like this. Yeah, so there's our ground state with two vortices. I think it's the ground state. It doesn't seem to be moving at all. So let's go ahead and check that energy, cd back a directory, go into Julia, and now we're just going to run the last Julia script. Calculate energy.jl. Give that guy a second to run, and let's check the angular momentum at the end here. So the angular momentum is 3.4. And what is it with the single vortex? Let's see if it's half. It should be half. We're going to let it run, and it should be half of that. I hope. If not, something real wrong is happening and I don't know what it is. Let me check something over here. I'm getting all these notifications. Nope. Okay. Okay, nice. So, again, if you guys have questions, concerns, anything like that, you want to talk about modern research, just go ahead. I'm totally willing to discuss just about anything. You know, sure, it might be academically themed, but anything really. Let me go ahead and get some water. Oh no, I have a drinking problem. Okay, this guy looks like it's done, so let's go ahead and run the Julia script. Should be over here. So again, the other energy was 3.4 times 10 to the minus 34. This one is hopefully 1.7? 1.98, that's not half. That is certainly not half. Okay. No, it's not. So that means that we don't have a good estimation. So the angular momentum energy here is somehow not... What I was expecting is if we have 2 units of angular momentum in the system. I was expecting the 2 units of angular momentum, which would be 2 vortices, to give us double the energy, right? Because now we went from 1 unit of angular momentum to 2 units of angular momentum. But that doesn't seem to be the case. There seems to be an offset, which could be equal to 0.3? Maybe? I'm not sure. So let me rotate faster. Because again, we showed earlier that with a rotation of 0.35, we get basically the same energy. We'll check the energy there, and we'll see if we can get any intuition here either. Again, maybe we leave with the unfortunate case where I actually don't know how to make a good test for this, which is super unfortunate, but you know, it is what it is. If there's no good test, there's no good test. Yeah, but see this? See this nonsense? Why did it go up to 1 times 10 to the positive 168? Why is that a thing? What is this? What is this nonsense? Why is it times 10 to the positive 169? What is going on? Is there an instability in the energy calculation that I'm just not aware of? Here we are 8.16, which is what it's supposed to be. But there it is again, 2.3 times 10 to the positive 169. What's going on with the energy calculation? For Pete's sake, is this a GPU problem? Like, is this specifically this GPU that I'm working on? Sorry for distracting. How do you think, is there any possibility to transfer information through quantum entanglement? Yeah, there certainly is a way to do that. It's known as teleportation. There's also, yeah, there's several other ways to do it. I mean, just performing a measurement, you can actually transfer information through quantum entanglement. It's actually interesting because it's the only known way that we can transfer information faster than light. But the idea is you just take two particles, and you you have one particle that they're entangled such that if one's up, the other's up. If one's down, the other's down. Which basically just means that if you measure one to be down, you know the other state's going to be up or something like that. It's just because you know how they're correlated, you know that they're going to have to be in that way. Plain user, thank you so much for following. Really appreciate it. Okay, so let me see. We don't have a good test for this. It seems to be that our energy is incredibly unstable. We get the correct energy sometimes, 8.16, so let's see if that's correct. But it seems like this energy is incorrect. No, that's definitely not the correct energy. 8.16 is incorrect here. So let me try... How do I do this? I mean, I could try lowering the resolution of the simulation to see if this is a GPU memory problem. It could just be that we don't have enough memory on the GPU to perform this computation. I don't think that's the case, because if that were the case, we would have been running into a whole bunch of issues just running this stream. And we'd have also run into a whole bunch of issues just before this that we haven't been running into before. But this did work on my Titan X's I had at work. So maybe it's an architectural problem. Maybe because this is an older architecture and the Titan X's are Pascal, that maybe it works okay? I'm not sure. Yeah, but it's not possible to transfer information this way because the process is totally random. At least I believe it so. No, it's definitely not random. You definitely have the way in the ability to create quantum circuits that are specifically for the process of information, specifically for the transfer of information this way. Einstein also thought it's not transportation, but already, what do you have, 970? Yeah, I have a 970. Einstein also thought that it's not a transportation, but and already determined before it was sent. This is a matter of interpretation. I mean, there's plenty of ways you can interpret it. I'm talking about the typical, I think, Copenhagen interpretation. I'm not really going to argue interpretations here. I mean, you'll get into heated arguments and no one's really going to have an answer. Point is, it doesn't matter the interpretation for the application. As long as you're doing quantum engineering and you're not worried so much about the underlying quantum physics, it's fine. You know, like, you don't have to worry about the interpretation. Very few people do, actually. Most people just use it for an application. This is so interesting that I know I was getting the right answer yesterday. I know these energies were correct yesterday. So 3.48 times 10 to the minus 33. What is it up here? 3.48 times 10 to the minus 33. 7.9. Oh, that's not correct. 8.16. Crap. Okay. Let me check GPU memory as we're running this simulation. So we're just going to watch NVIDIA SMI. SMI. And let's see what we got here. SMI. And we're going to watch that and we're just going to run it. Strawberry Jesus 11, isn't it like opening a sealed box after sending it to, let's say, Mars? You can kind of transfer into like that one time, but no further communication happen. No, it's proven to be wrong. Google Bell's theorem. Yeah, so yeah, this is another thing, right? The Bell inequality. It doesn't look like the GPU memory is increasing at all. It looks like it's the same. So I'm gonna guess, 5.7. Is it gonna go to 5.8? Let's just, it's 5.7. Let's see if it goes to 5.8. I mean, maybe there's just, I mean, the volatile memory is 99%. So maybe there's an issue here. Well, here all the energies are fine. 8.027 is not bad. It's not exactly what we're looking for, which means the calculation is slightly wrong, but it's the right order of magnitude. So what happened last time? Why was it so crap? Huh. Isn't it like open a seal? Okay, so this has to do something with volatile GPU memory. I have no idea what the case is. I don't know why this is the case, but you see, there it is again, right there. T equals 0, 2.48 times 10 to the 169. Sometimes it just craps out. I don't know why the energy calculation craps out like that. I don't know what you mean, Strawberry Jesus. Isn't it like opening a sealed box after sending it to, let's say, Mars? You can kind of transfer info like that one time, but no further communication can happen. Yeah, in some ways, yeah, that's true. Because after the measurement, it's not that you can go back before the measurement. Measurement of a quantum state is considered an arrow of time by some people. The idea is that you can't reverse this particular measurement. You break the entangled state. Yeah, that's true. That's core usage, not the memory. That's true, I guess. Yeah, you're right. So it should be fine. Yeah, actually, we want the GPU memory to be like that. Oh, man. Oh, man. It is an information transfer. There's no question. I mean, you're transferring one bit of information to another bit of information. What's the time complexity of the algorithm working on your data? It is n log n for the most part, because if the FFTs are going to be the most, yeah, it's n log n. You're barely using any memory. You are correct. So I have no idea why it does that then. Why does it sometimes crap out? Let me run it one more time. I'm just going to watch the energies. So your energy is 3.4 times 10 to the negative 33. Let's check the next one. 3.4 times 10 to the negative 33. I'm okay with that. Still fine. Next one. 8.027. Yeah, these are all fine. What was going on? Why were we times 10 to the positive 169? And why can't we replicate it? The fact that we can't replicate it and I'm running the same command is the thing that kind of gets me. Also, this energy is not right. I don't know why the energy is wrong. I got the energy to work yesterday. And now it's not right anymore. Oh my gosh. I thought we had it all fixed. But no, it's clearly still broken. Is this because the vortex is going in the opposite direction? Or is this because maybe we're not yet in the ground state? Maybe it's because we're imprinting the vortex. And maybe that imprinting process... Let me try running this without imprinting a vortex. Okay, so we just do this. And let's check the energy there. And then we're going to check the energy with Julia. Q there. Control C, whatever. Single-use info transfer with speed less than or equal to the speed of light. What is the complexity? You're barely using any memory. Yeah, single-use info transfer with speed less than the speed of light. Well, no. I mean, the speed is instantaneous, right? The problem is that... So here's the problem, right? You do the measurement, right? So if you measure one state to be up, right, then you know the other state is down, right? But the problem is you don't know the other state is down until after the communication over here happens, right? So you've got to transfer that information over here, and that transfer is speed of light, right? So at best you can do speed of light, but the thing is, in principle, the measurement of an entangled state will force this other state to be down even before the measurement occurs. There's some experiments here, but honestly, this isn't really my area. I mean, I do quantum stuff, but this really isn't exactly my area. So let me go ahead and run the Julia code here. So we're just gonna run Julia calc energy. I don't do too much with entanglement. I mean, I know about this area, but it's not really my thing. 7.7869. Okay, that looks fine to me. Let's go ahead and run it one more time with a higher omega, such that we generate a very large number of vortices, and we'll check the energy there. And then we're going to be in this very weird case where for some reason, when we imprint a vortex, it does something different than when we don't imprint the vortex. And I have no idea how to fix this case. No idea whatsoever. Dag nabbit. It's okay. We'll figure it out. Together. No, we won't. I've got a feeling this is just going to be one of those unsolvable mysteries, you know? Like, we'll be on a television show in 20 years, and people will be like, yeah, back in the day, there was this one guy trying to calculate the energy of a quantum state, and he couldn't do it. Yeah, that's fine. This is fine. So we're going to look for an energy of 1.12 or something times 10 to the negative 32 from the Julia. How would you define your area in simplest terms? I would say, okay, so I do mainly computational physics. That is to say, I create and develop methods to solve physics simulations of various types. For the most part, I've been focusing on quantum simulations, but I've also done plasma physics and several other things. For the record, this is quantum simulation, not quantum information. The difference here is that for quantum simulation, via classical computers, we're basically developing methods to better understand experiments and stuff that could lead to quantum information, but for now we're just trying to get a better understanding of the underlying quantum stuff. And for me in particular, I'm working with superfluids, which admittedly is quantum, but it's more fluid dynamics than it is quantum. Does that make sense? Like, I worry more about vortex structure than I do about the fact that we're dealing with an actual wave function here. And this is kind of the stuff that I do. So I develop more methods, massively parallel computing, supercomputing, this type of stuff. So high performance computing. That's what I do. More than I do, I would say, again, superfluid stuff. Like creating two black boxes with the same or correlated info inside and then opening those at different locations. Yeah, you are correct. That's exactly what it's like. Arts99, thank you so much for following. Really appreciate it. By the way, there was someone who subscribed the other day and I missed that subscription. If that was you, let me know, because I apologize for that. I don't think it's you. There's two people. I think it was Case and Twitch and JBZ55. I think I missed them. But if they pop up, let me know, because I accidentally missed them. Okay. I mean, I know it wasn't you in particular, but it's just a general question to people watching this chat, watching the stream. Okay, so let's go ahead and run this real quick. There it is. Look at that. 3.54 times 10 to the positive 169. Okay, so we're going to run Julia calc energy. And what we want is an energy that is 1.1. Crap. I was like, let's look for an energy that's 1.1. 1.2. Crap. Okay, so then there's something still wrong with our energy calculation. I swore we had it right, but there's something still wrong. So let me go ahead and plot these guys, and we'll just mess around, see what we got here. So let's cd into pi, and let's just go ahead and do the last Python plot, and we'll get this energy calculation figured out. Come on, there you go. Here's our vortices. They're all kind of doing their thing. Yep, great. Okay, so our final state looks like this. This just has a whole bunch of vortices randomly scattered in our Bose-Einstein condensate. Colors? Yeah, sometimes we have colors on stream, sometimes we don't. So again, this is representing, looks like 5, 6, 7, 8 vortices in our Bose-Einstein condensate. That means we have 8 units of angular momentum. I don't know how that helps us at all, but we have 8 units of angular momentum. And again, units of angular momentum here are very vague. As we said before, it's difficult for us to say that a unit of angular momentum has X amount of energy. That is certainly something that we need to kind of figure out. Okay, anyway, we're working on this. So we've got this vortex structure. let me see if any of these energies are close to the same. So I'm just going to scroll up here. Let me just clear the terminal a couple times. So we're just going to clear, and we're going to run this Julia script one more time. CD back into Julia, and let's run it again. And I'm just going to check to see if any of the energies are roughly the same. Okay, and then we'll check the energies and we'll see what happens. Okay, so looks like for a while we've got this 1.2 state. Let's see, so we have 8.69, 8.69. So it looks like it's fine. 3000, so 3.36, correct? The next state though, t equals 0 is 3.36. Okay. T equals 10,000. Huh. Interesting. So here we're saying t equals 0, we have an energy of 3.36 times 10 to the negative 33, which is precisely what we see here. Then when we read it into the external script, GPUE is outputting 3.336 times 10 to the negative 33 for this state, but this external script is saying 8.69, right? And then we have the same thing down here, it's 20,000, right? 20,000, but down here it's 8.69, that's fine. 8.69, again, that's fine because there's two 8.69s, but it's delayed by one step, it looks like. It looks like there's, all the GPU output is off by one. And then finally it's wrong at the end here. So let's see what we have here. 1.26, 1.126, 1.218. Yeah, we're definitely off by a bit. More than that, these energies down here should certainly not be the same energy. You know, they should be changing because the state's changing a bit. But they're identical. There's literally no difference between any of those. Meanwhile, this guy shows slight variation between the three energies there. Ah, crap. Hey, CSK Meek, how are you, man? Yes, energy, I see. But no, there should certainly be a difference in energy. There's something weird happening on this GPU that wasn't happening on the GPU that I had at work the other day. So I don't know if this is a GPU-specific problem. Maybe it is. Maybe this is something that's only happening because I'm running a GTX 970. Maybe if I run this back on the Titan X's, or if I run this on the P100s we have at work, maybe it'll be fine. But then the question is, why is it failing with a GTX 970? What's the problem here? Is it floating point precision? There's no way we have an instability so large with floating point precision that is going to give us something times 10 to the positive 169. GPU are not powerful enough. But the thing is, when we checked this, we weren't really even using that much GPU memory. It's not like we were actively using all the GPU cores, but we weren't really using that much GPU memory. There was something that came up the other day, now that I'm thinking about it, a long time ago, GTX 970 fault. There was something that came up. I don't remember what this is. GTX 970 faulty. Something was mentioned. I remember there was something wrong with the cores. Maybe you should try using bigger precision. Yeah, so I can use double precision at work. But the problem is with CUDA cards in particular, you really only get double precision when you deal with the Tesla series, which is the compute series. Rala Java, thank you so much for following. I always wondered, isn't uncertainty principle just us being unable to perform adequate measurements? I mean, like, isn't it like measuring info about golf ball via hitting it with another golf ball? Maybe in some point, I'm not sure. So there's this thing, it's called Bohmian mechanics? Something like this, which basically is a way for people to understand quantum mechanics without the quantum weirdness that you would expect. It's basically explaining quantum behavior as entirely mathematical constructs. It is something that you can look at, and it's something that's very interesting. But again, I don't want to go so much into interpretation here, because this isn't really my area. I mean, again, I do quantum stuff, but the interpretation of quantum mechanics is not something I really want to discuss too much. It's cool, don't get me wrong, it's very interesting. Quantum is very weird, but it's not something I want to go into this. Bomb de Broglie? Yeah, we can take a look at that. But unfortunately, I mean, again, this is a research stream. I'm kind of streaming for work. It's very interesting. It is undoubtedly very interesting, but this isn't exactly my work. It's not really too related. And as much as I hate to say it, I mean, sure, quantum is incredibly interesting, but it's just not, it's not what I'm good at. I'm better at doing like simulations of quantum systems. I'm better at like GPU computing, stuff like that. I don't know how to put it. I don't know how to put it. It's the one you call Bohemian mechanics the same. Yeah, I know this is the same. Okay. Hey, said who 12, how are you? Okay, so my best guess is that the energy calculation is somehow screwing up on my GTX 970. What are you doing? I'm doing calculations of superfluid systems. So just for the record, because I have to plot it anyway, I'll go ahead and plot it again, because I'm going to take a look at this anyway. So let's do Python plot here. So this is a quantum superfluid. The idea here is that, you know, as you move the simulation forward and you're trying to find the lowest energy state, you eventually get all of these vortices in the system. These vortices are just like, they're tornadoes that are piercing your condensate from the top to bottom. And the idea is that we're trying to find the lowest energy configuration for this. What I need to figure out is how exactly I can find the precise energy of this. And I don't know. I don't know how to find the energy of this state. So that's where I'm at. I'm trying to find the energy of this. What do we have here? Quite short shaders too. Is this wave-like? I know Broglie said some shaders about you should also make sure you're right. You're working on the top of the right. Working on the top of the right commit or branch. I can check real quick. Because I know this is working at work yesterday, but I'm pretty sure I pulled it, everything. Get pull, origin, energy fix. If I'm not working on the right, this is going to be really embarrassing if that's the problem. Now, we're already up to date. Let me just do a git log just to make sure. Git log. Working, there, I even wrote it, adding working energy calculations in GPUE. I mean, that's definitely the last commit. I mean, no doubt, on an iPad, sorry. No, don't worry about it, man. I appreciate that you're chatting at all, honestly. Like, you're super helpful. Let me go ahead and check this this forum stuff over here. Tom's Hardware. What I'm looking for is a faulty GTX. PC randomly blue screening, GTX 970 graphics cards. I think that's the same one as down there, isn't it? I'll take a look. Okay, do you guys hear something? I'm going to check my sound real quick. Oh, you can definitely hear that. Okay, so there are people outside that are mowing the lawn, and I can't really do anything about that, so I'm sorry. No, that doesn't seem to load. Faulty NVIDIA fan issue. It's not a fan issue. Recursive fault error. I'm going to look for CUDA cores. Maybe? I don't know. You probably can't hear it over the music, honestly. GTX 970 specifications. Okay. Well, okay, so there's something going on with this energy calculation. I don't know what it is, and I'm afraid to do it further on this GPU because this GPU is producing dramatically different results than previous GPUs. Is it related to the electromagnetic field? Is what related to the electromagnetic field? Hey Ramu, by the way, I don't know where you came from. Hi, how are you? Let's see, what do we have? SSH into Office? I could, but I've got a feeling SSHing into the Office would probably be a security risk of some sort. Okay, so, okay. For the record, this should work just fine on a GTX 970. There's no reason it shouldn't. And we know that this energy problem is going to be coming in from either the interaction energy or the rotation energy. I'm like 100% sure it's going to be coming in one of those. So what I'm going to do now is I'm actually going to run it forward a little bit in real time here. So we're just going to do 10,001 steps in real time, and we're going to run these energies. GPU not strong enough? I don't know, because we're not really using that much of the GPU. We're using very little of the GPU memory. Here, let me just run NVIDIA SMI, but there we are, 168. So let's do watch NVIDIA SMI. Yeah, so sometimes it just craps out. So here it is again, 169. Why is it 169? I think I know why. I think I know why. I think my derive function is probably grabbing a random element in GPU memory rather than grabbing the appropriate. Okay, here we are. We clearly are having problems here. Here's a plus 169. So what I'm going to do is I'm going to go ahead and Control C out of here, and I'm going to comment out that part of the energy calculation. So I'm going to comment out the angular momentum energy, and I betcha it's going to be fine. So we're going to VI into source, and then we're going to go into split op, which is where I put it, then energy calc down here, and I'm just going to comment out the that part of the energy calculation. There's GPE. This one should be fine. This is the guy I'm going to comment out. So again, just a long comment, just because I don't feel like messing with the code itself. And then it should be down here, I believe. Okay, break that. Go over here, we're going to make that, and we're going to run it again. And we shouldn't see these 169. So we'll run it a couple times because this is unstable, but it must be that my derive function is grabbing a random element of GPU memory. That must be the problem. Maybe this is one other position, like floating point operations. Haven't rerun anything like this, though. That's true. The main issue is that the Titan X that I was running at work is still floating point precision. Maybe we should get a GTX 2080 Ti or Titan Z. Yeah, so I think what I have at work is fine. I've got plenty of good GPUs. This is, again, just for mainly debugging and testing and development and stuff like that. So it's not that big of a deal. Okay, one second. I'm checking a notification from my boss real quick. Okay, good. Okay, it seems fine. Okay, do you work at NASA? No, I don't work at NASA. I work at the Okinawa Institute of Science and Technology. It's a science institute in Okinawa, Japan. It's a nice place. If you have a chance, I'd recommend you go there. Do you work at NIST? No, it's OIST, O-I-S-T, not N-I-S-T. Some specific hardware gives you better performance via sacrificing precision on floating point ops, but they don't do that at GPUs. Yeah, so for the Tesla series, they allow you to do double precision calculations. Okay, so we didn't see anything times 10 to the 169 there. So what I'm going to do is I'm going to pop up here and I'm going to comment this back in. And let's go ahead and make that. The only problem is this C++. It's CUDA, so it is, yeah, it's C++. It's CUDA C, so it's a bit weird. It's definitely not Julia. This is C++. What is this, OpenCL? It's CUDA code, just CUDA. No, nothing crazy there. So I'm watching the energies here, and I'm going to see if we have something times 10 to the 169. I'm not seeing anything so far. It seems fine. Crap. The problem is with these errors, I can't easily replicate them, right? Like, you saw it. You saw it right there, and we reran it, but I don't know where it'd be coming from. So it must be in the derive function. I'm 100% convinced that I'm doing something wrong with the derive function. So let me check that function real quick. So I'm going to VI source and kernels. And I've got this derive function here that allows me to perform a derivative along the x, y, or z direction. So it allows me to do a del operation, d by dx, d by dy, d by dz. Why all scientists use Python? I would argue I know very few scientists that actually use Python. There it is, 169, right there. Oh, you are moving slow, my friend. GPU. Oh well, that's fine. Maybe I'm just flooding GPU memory. I don't know, because it didn't say I was. It seemed like I was using very little GPU memory. I don't think anyone uses Vulkan for science stuff. Isn't it like a graphics only library? Yeah, so as far as this is concerned, you're totally right. So for GPU computing, pretty much everyone uses CUDA. Some people use Python for, it depends on what you're doing, right? I'll just draw this out real quick. Page, new page before. You've got various different scientists who program. So we'll say scientists who program, scientists. Programmers, coders. You have the HPC people, and then you have the theory people, and then you have the experiment people. These are that I know of. All right, so we'll say HPC. Well, I should just say computational. So we'll say computational, okay? And this is from physics, so just forgive me here. Theory people usually use Python, MATLAB, and sometimes a few of them use Julia nowadays. But it's rare. Most people use Python, MATLAB for this. Then you have the computational people. They use predominantly C, C++, Fortran, or some sort of GPU thing. So this is probably CUDA. These are what we see for the most part. They'll also use OpenACC, and then they have other languages that allow for them to kind of interface with the theory people. So for these, they'll use Python. Or OpenACC. These guys also use MPI. So we'll say MPI for multi-threading and stuff like that. So then they usually will create an interface in Python so that the theory people can use them. The experimental people are probably using MATLAB or LabVIEW. These are the languages that I see most, but I mean, there are variations on this. What is here? I finally found it. I called weak measurement, not soft. Oh yeah, weak measurement. I know what you're talking about. Let's see, because Python is easy to use. Yeah, so for theory, people use Python a lot. What do we have here? So a PhD, write Python while working on low-level hardware. You can do compute. Let's see. I'm not really happy with Python dominating machine learning because of scientists who love Python. I'm a dev and engineer. Fair enough. Like, I also don't like Python being particularly used in this area. But it's just, it is what it is. You know, Python is taking over for machine learning. You have Flux with Julia, which is promising in terms of performance, but really and truly, Python is the king here. And there isn't much we can do about that. Now, my parents did Fortran. A lot of programmers, a lot of physicists still use programs. Fortran. Yeah, please be honest. I mean, what is the world without honesty? So C, C++, Fortran. These are the main languages that I see, but I might be missing a few. And this is for wah wah. What are we talking about? Wah wah. Okay. Control Z. And again, these are for scientists. Bearable kappa. I feel like I'm missing something. I feel like I'm definitely missing something. Okay. So those are the languages I see scientists use all the time. I'm gonna look at this derive function. I don't see what I could possibly be doing wrong here. I'm gonna say if GID plus stride, Python dominating the machine learning space makes little sense even to me, and I love Python to death. Baby crying? No? Oh, okay. I see what you mean. What is a world without honesty? Bearable? Oh, okay, fine, fair enough. I guess a lot of people lie. So for this derive function, what we're doing is we're trying to create a derivative along x, y, or z, which means we're reading in some sort of stride that allows for us to perform that derivative, right? So if we're performing a derivative along x, we're going to basically be looking at components that are right next to each other. If we're looking for a derivative along y, we'll do an x dimension away. So they're this far away, then this far away, then this far away. For along z, it's x times y dimension, right? So because of the way we've indexed this, there's particular strides that we have to deal with. Now, I have this big if statement. I'm sorry about that. I hit the microphone. I have this big if statement that basically said if GID plus stride is less than grid size, so it has to be less than grid size, we're going to say the output is going to be a GID plus stride minus GID over dx. Should be fine. And then otherwise, all we're going to do is we're going to take the current GID that we're on. I guess let me also do the following. I'm also going to say and GID is less than G size. That's not right. Less than G size. So this means that if GID plus stride is less than G size, we go into this loop. And if GID is less than grid size, we go into this loop. Wait, I need to think about this. We actually found a paper out measuring quantum info. Let's see. My problem with people with a PhD or doing masters using a language like Python instead of something more difficult is that people are dying just to feed themselves, having to look at trash, sleep outside, negative 10 degrees, etc. What are we doing? We whine about how difficult it is to get anything done to work in C and C++. I don't know about scientists, but at my last job, engineers who were getting into machine learning were all using Python. Respect, man, for doing CUDA. I understand what you're saying, but I do also feel like that is a bit of a bad comparison because I mean, Python helps people do things faster. If you're a scientist and you want to revolutionize the world, you know, you're doing theory. Here's the problem. Most physicists don't believe this is an actual area of research. So they don't believe this is an actual area of research. They believe that this interplay between theory and experiment is the most important, right? Because they think that you create something theoretically, and then after it's created theoretically, you then experimentally validate it. Or vice versa. You find something in experiment, and this propels the theory forward. And through this interplay between theory and experiment, you move the world forward. They don't care about poor people. They don't care about anything else but the movement of human knowledge forward. So to them, Python, MATLAB, Julia, these are perfect languages because it allows for you to move this cycle faster. That's what they want. They want to move this cycle faster. And Python, MATLAB, Julia, these are things that allow you to move that cycle faster because it's easier. GLD is sadder. Let me talk about that in just a second. The thing is, these guys are the guys that allow these interfaces to be fast. So I think that's okay. I think the way it is currently set is okay. I agree with you. I really wish more scientists were better at programming at lower level. Like, I really wish we had more C++ programmers. I really wish we did more GPU computing, but it is what it is, you know? Python is less than or equal to Java, or less than JavaScript. What is this with CSS all of a sudden? No one uses CSS for computation. Can confirm. But Sedhu, I do understand what you're saying. I feel like a lot of people are whining about things they shouldn't whine about. They're whining about the fact that, you know, oh, we have to use, or we're not going to use Fortran anymore. It's too difficult. Let's use Python. I get that. And I wish it was better. I wish more people did low-level programming. But, I mean, it is what it is. I mean, they don't care about low-level programming because, again, they're just trying to get this cycle faster. That's what they want. All this programming is just a waste of time for them. You can use CSS for computation, calc x times y. I'm sure you can. Let me think about this. So if GID plus stride is less than grid size, right? Then we want to go in here. But if G size is less than, if GID is less than grid size, then we don't want to do anything. Yeah, we don't want to do anything. It's not possible. Scientists have enough work with science stuff. It's just that scientists are working in combo with coders, and coders should get some insight in science. This depends. There's actually a very big area of scientific software development that really needs to be discussed a bit more. And this is kind of the area that I know a good bit about. But honestly, scientific software development is just not at the stage. Like, it's currently not understood whether a scientific software developer is a scientist or a software developer. And because of this, they kind of have to play both cards. They have to publish regularly because they have to keep, if they don't publish regularly, they lose their job in science. But at the same time, they don't make nearly enough to be a good software engineer because they make less than, they make scientist salary, right? So it's kind of like, you know, if you're going to be a software developer, be a software developer. Don't deal with scientists. If you're going to be a scientist, you know, they don't care about software development, clearly, because they don't pay their software developers nearly enough. And also, they treat their software developers as if they're scientists, you know, since O n to the 4. My last homework for digital image processing had us code a 2D Fourier transform on 1000 by 1024, and the naive approach in Python and MATLAB would take literally years to execute. No, how are you telling me that the numpy.fft.fft2d is an n to the 4? No, that can't be done. That's a DFT. That's not an FFT. An FFT should be O n. It should be O. Analog, right? 1 second. Let me think. Oh no, you're right. You're right, because the DFT would be n cubed for a simple operation. But it should be n squared log something. I don't think it should be n to the 4. That seems way too high. How can you use science computation if you can't operate on transcendental numbers? It's like exactly 100% of numbers. Wait, what are we talking about here? I mean, literally translating the math formula into for loops. Oh yeah, that's bad. That's certainly bad because that's a DFT, right? That's not an FFT. An FFT requires like some weird. Yeah, so that's going to be n to the 6th, isn't it? Because each matrix multiplication is n cubed. Maybe, I don't know, I have to think about that. Let me think about this guy over here. So void derived, we say GID plus stride is less than G size, right? And GID is less than grid size. Is that what we want? Basically, the problem here is that the GID could go beyond the size of the grid, right? And so my guess as to what we're doing is we're accidentally grabbing elements that are beyond the grid size. Right? So I don't want to grab that element. So we're going to say GID plus stride is less than grid size. So that means we're not going to grab that. And GID itself is less than grid size. So what we'll say then... Okay, I see the problem here. Yeah, you're right. So what we're going to want to do is put an if statement over this whole thing. So we're just going to do an if statement out here, unfortunately. So we're going to say if GID is less than G size here, and then we're going to pop down here. Yeah, that should be it. Else if GID is less than grid size. Oh yeah, we could also do that. Let me think. Else if, do we want an else if? 1 second, I have to think about this. So it's going to be if GID is plus grid size, plus stride is less than grid size. If that's not true, I know this should work. This is fine. But can we use an else if is the question. Okay, so my point is I saw some little girl, 13, do photorealistic paintings in a video, and a man eats steel from old airplanes. Well, what we do, we try to remove all pointers from languages. I mean, look, you're not wrong. We're doing some really weird stuff. But at the same time, like, I am against the idea that removing pointers from languages is somehow less important than eating steel from an old airplane. Like, sure, if you're trying to push the body, you're trying to push the humanity as far as we can go. Sure, removing pointers from, you know, a language seems annoying, but like at the same time, it allows you to do that cycle faster, you know? Like, it seems fine. Okay, whatever, let's go ahead and run this. I know this is dumb. I'm sorry. We're just gonna do if GID is less than G size. And we're just gonna pop this down here. We're just gonna do the same thing. I'm sorry. We're gonna run that, go over here, make that. So now we cannot be performing the derivative outside, so we cannot be grabbing random GPU memory. Let me run this, and let me also, real quickly, just check to make sure I commented this in. So let's go into VI source, split op, and let's go down to energy calc. Pop down here. Yeah, it seems fine. There's also non-computable numbers like Chaitin's constant. Our simulations nowhere near to real life. This is true. I mean, undoubtedly, simulations are not real life. Remember, use goto, macros, pointers, and needles to poke binary. Crap. This is the thing I don't understand. Some time steps are okay, but other time steps are not. Okay, I might need to run this. Why is this not working on this GPU? That's absolutely insane that it's not working. Like, what is going on? Am I accidentally using cores that are already being used for visualization? Is this my problem? Is it just because I'm using the same GPU for... I don't know. I have no idea. Because it's working, right? We're getting the right physical result, but the energy calculation is way wrong. So, why? That energy calculation is way wrong. Real men shoot someone's head, but not to kill them, but to give them a haircut. I mean, I don't think I've ever seen a real man do that. So I'm not sure if that's exactly true. Crap! This is all wrong. All we've done today is fix the one rotation thing, which granted took us a while, but I just can't figure out anything further. Take a 5-minute walk around, go grab some water, maybe it will be clear when you come back. Could be. This is gonna bug me to death. Why does it not work? Why does this particular function not work? I did build it, didn't I? I definitely built it. Let me build this one more time. Nope, it's built. There's no question it's built. And I definitely wrote it in there. So we know that the derive function. So my initial guess was the following. My initial guess was that new page before. I have this function called derive. And my initial guess was this derive function. My initial guess was that, I was grabbing these elements for my GID, and I was accidentally grabbing extra elements, right? So I was accidentally grabbing areas in GPU memory that were beyond my grid size. So I thought that was okay. Could be something wrong with your display function. What do you mean display function? df by dx? Yeah, this is what we mean. It's just d by dx, but it allows for a derivative along x, y, or z for a 3D array. You'll get into a rabbit hole of doubt and problems, and you'll lose much more time if you stick into it. That's my opinion. I've lived that kind of problem way more times than I want to admit. Dude, I know, but I've got to get this working. Because honestly, I've been working on this energy calculation for literally 3 weeks now, and I'm just now getting somewhere. And it seemed to work yesterday on my Titan X, and it seemed to work yesterday on the K80s, and it seemed to work yesterday on the P100s, but it doesn't seem to work on my good old-fashioned GTX 970. Am I building it for the wrong architecture? Do I have an architecture in here? 3.7. What is the architecture of a 970? CUDA. Should have a Wikipedia page there. Let me just look for 970. It is GTX 970 is a 5.2. We are way beyond. I'm going to build it for 5.2 architecture and just hope and pray that this somehow fixes it. So I'm just going to put a 52 in here. We're going to put another 52 in here. And we're going to see make dot make clean make J4. Let's go. This isn't going to do anything, but I'm just desperate at this point. But why use Windows 2000 theme? If this fixes it, it's going to be funny. Look, this can't fix it. There's no way this is going to fix it. I'm lost. I have no idea what I need to do at this point. What do we have here? Oh, okay. Beshaliv, thank you so much for following. Let's run it. Crap. Is there anything like DFX in CUDA? There's not really that I know of. I wrote my own function. If this fixes it's going to be funny. That might be it. I'm not sure. Check with the change via version control. I mean, I can do a git diff, but there's nothing that's really different from what we put on last night. The only difference is that this is working now. No, it's not working now. Well, I mean, it's not working now, but it's not working. Does that make sense? Like, it's doing the same error we had before. We don't have any times 10 to the positive 169s yet. That's nice. Maybe it's the actual calculation. Well, that's the thing. Maybe we know that we know that the error is coming in from the energy calculation for the angular momentum. Maybe you're casting different types. Could be. I could be. 1.109. You should probably fix those. May be used before assignment warnings. I can't do anything about those. You're talking about these guys up here? Yeah, oh, wait, are you talking about these stack sizes? Are we talking about the may be used? That's a problem. Look at my mouse, guys. That is crazy. It's gonna be 169 down here. No, okay. Somehow that worked. I'll run it again. No, but so these stack sizes here, that's a bit of a problem. Maybe used without sign doesn't mean anything. The C++ compiler being stupid. There are some things here where the C++ compiler is being stupid. These guys in here are specific GPU warnings because I'm using a recursive function on the GPU that it doesn't like, but there's no way around that. There are some other guys in here that we should probably fix. In fact, I should probably go through and fix all the warnings. I definitely should. That's a good thing to... Thanks for that. I should do that. Before the stack size. Vortex 3D init CU is used before its value is set. These are all because of the way I'm initializing it, I think. But let me check just to be sure. So let's go into VI source init. Let's go to 342. Par.store. Oh. Yeah, this is what I want. So the point was that I wanted to initialize a... this was what I wanted here. It was bad code design. Undoubtedly, it was bad code design, but this is kind of what I was hoping for. I just wanted to create a pointer here. It was the initialization. And then I was going to fill the pointer in later. Admittedly, bad code design. Definitely bad code design. It's just kind of what I did. Making variables without initializing it in C++ means you're likely using garbage. Undoubtedly, I'm using garbage here. I wanted to initialize the pointer on the GPU so that it existed, and then I was going to allocate that later. Bad code design. Undoubtedly bad code design. But... should be okay. Okay. Well, it didn't seem that we had any times 10 to the 169 errors. Let's try running this again. I'll fix the warnings in not today's stream. I'll fix the warnings later. It's going to take forever for me to fix those warnings. You should initialize whenever you want. This is kind of, it depends on who you are. Somehow fixing the architecture seems to have fixed my energy calculation a bit. It's still not the right value, but it's not the right value anymore. Does that make sense? We're not getting incredibly bad results. We're now getting results that are kind of okay. You should initialize... Wait, what are we talking about, Sedhu? I'm a bit confused. Crap. So let me check the Julia energy real quick. Come on, stop double-clicking. CD back into Julia. Oh, CD just into Julia. Why? I don't know what's happening at all, guys. I'm just going to run Julia. Let's go. Okay, so now the issue is that the energy that I'm calculating from the GPUE is different than the energy I'm calculating from my external script. And I trust my external script, but I'm not sure what's going on there. Okay, so I'm not sure how there's one that goes. Yep, you're right. It goes to 169 there. Okay, I have no idea. So what I might do today, guys, is I might go ahead and close stream for now. We've been streaming for about an hour and 30 minutes, or sorry, 2 hours and 30 minutes. I think it's okay for a stream. So I think we'll go ahead and close it here. I'm going to run this at work, and I'm going to see what problems we get. So we know currently the following. We know that when we imprint a vortex, for some reason the energy is different than when we don't imprint a vortex, right? So we know that's a problem. I don't know why it's a problem, but we know that's a problem. So I'll be back tomorrow from 5 o'clock a.m. Japanese Standard Time, typical time for streaming, where we'll still be working on algorithm archive stuff, and then I'll come back for this stream again at 9 o'clock a.m. Again, it'll be maybe 2 hour to 3 hour stream, something like that, where we'll be working at this. So right now it's 11:30 a.m. Again, I'm going to start 2 hours and 30 minutes before this time tomorrow, and that's what we'll do. I'm really going to try to iron this out tonight, or this afternoon, and we'll see how far we can get. So guys, have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. Let's see who's online that we want to host at the end of stream. Deadflip, Lana Lux, Dowright, Mr. Orologist. We could do Go Pirate Software? No, Lana Lux. Let's do Lana Lux. That seems fine. So anyway, guys, have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I will see you around next time for the next episode of Simuleos. I hope you guys have a wonderful time. And again, I'll be live at 5 o'clock a.m. Japanese Standard Time to do my typical algorithm archive stream where we'll be working on the plotting chapter. And then I will be live again at 9 o'clock a.m. Japanese Standard Time where we'll be doing the GPUE development stream. So if this is interesting to you, please come back then. Have a good night. I came from there. Oh, okay. So Mr. Joe, Jeff Leff, thank you so much for following. Thanks again, guys, and I will see you next time. Bye, guys.